Light moves at a constant speed, about 300,000 kilometers per second. But why can't anything go faster? The answer lies deep in the laws of physics. Einstein's theory of relativity showed that the speed of light isn't just fast, it's a cosmic speed limit. Nothing with mass can reach it. As objects move faster, they gain energy, and near light speed, that energy becomes infinite. It would take endless power to go faster than light, which isn't possible. This limit shapes how time, space, and even gravity work. It's why we see the universe the way it is. No matter how fast you go, light always moves away at the same speed. It's like the universe has built-in rules that everything must follow, and light speed is one of them. The concept of light and its nature has puzzled thinkers for thousands of years. Before modern science, understanding light was intertwined with philosophy, religion, and the very definition of human perception. One of the most basic questions was whether light appeared everywhere instantly, or if it took time to travel from one point to another. This debate, seemingly simple, laid the groundwork for complex scientific inquiries that would span centuries. In ancient Greece, roughly 2,500 years ago, philosophers pondered how we see. Empedocles, a Greek philosopher from Sicily who lived around 490 to 430 before Common Era, proposed one of the earliest known theories. He believed that light was not something that came from an external source and entered the eye, but rather that vision occurred because a special fire emanated from the eye itself. This fire, which he called the effluvium, would then interact with objects, allowing us to see them. Crucially, Empedocles also suggested that light was composed of tiny, rapidly moving particles. This was a radical idea for his time, implying that light had a finite speed, even if he did not propose a method to measure it. His emission theory, while incorrect about how vision occurs, contained an early inkling of light as a travelling entity. Plato, another influential Greek philosopher who lived from approximately 428 to 348 before Common Era, built upon some of these ideas. In his dialogue Timaeus, Plato described vision as a process involving three components: an internal fire from the eye that streamed forth, external light from the sun, and light reflected from objects. These three fires converged, and vision occurred at their point of union. Like Empedocles, Plato's theory also involved light moving or streaming from the eye, implying a process over time rather than an instantaneous phenomenon. However, the exact nature of this movement and its speed was not a central focus. For Plato, the philosophical implications of vision and reality were paramount. Euclid, the renowned Greek mathematician who lived around 300 to 275 before Common Era, focused less on the physical nature of light and more on its geometry. In his work, Optics, Euclid established the principle that light travels in straight lines. This was a significant observation, fundamental to understanding shadows, reflections, and the design of lenses and mirrors. While Euclid did not explicitly state that light had a finite speed, the concept of light travelling in a specific path, rather than simply appearing, subtly reinforced the idea of it being a physical phenomenon that occupied time. His geometric approach to light laid essential foundations for later optical studies. Aristotle, arguably the most influential ancient Greek philosopher who lived from 384 to 322 before Common Era, held a different view. He argued that light was not a movement of particles or waves, but rather an actuality, or quality, of a transparent medium. For Aristotle, light was the state of a transparent medium being illuminated, rather than something that moved through it. If a medium was transparent, and a light source was present, then the medium became lightened. This perspective naturally led to the conclusion that light's appearance was instantaneous. There was no journey to be made, no speed to be measured, because it was a state, not a motion. Aristotle's immense influence meant that his view of light as instantaneous largely dominated Western thought for over 1,000 years. His authority was so great that challenging this idea was a profound intellectual undertaking. After the decline of the classical Greek and Roman empires, scientific inquiry in Europe entered a period of stagnation. However, significant advancements were made in the Islamic Golden Age. One of the most pivotal figures was Ibn al-Haytham, known in the West as Al-Hazan. Born in Basra in what is now Iraq in the year 965, Al-Hazan was a Persian polymath who made groundbreaking contributions to optics, astronomy, and mathematics. He meticulously challenged the Greek emission theories of vision. Through careful observation and experimentation, Al-Hazan correctly proposed that vision occurs when light from an external source reflects off objects and then enters the eye. This was a profound shift, placing the source of light outside the observer. Al-Hazan's work, particularly his monumental Kitab al-Manazir, Book of Optics, written between 1011 and 1021, was revolutionary. He conducted experiments with pinhole cameras, demonstrating how light rays travel in straight lines. While he acknowledged that light must travel, he too struggled with the immense speed of light and did not conclude that it had a finite, measurable speed in the way later scientists would. He understood that if light was instantaneous, it would not explain certain observed phenomena, yet he did not definitively state it had a measurable speed. Nevertheless, his empirical approach, emphasis on observation and experiment, and his correct understanding of how vision occurs were critical steps forward, moving the study of light from pure philosophy to experimental science. His work influenced European scholars for centuries after being translated into Latin in the 12th century. During the European Renaissance and the scientific revolution of the 16th and 17th centuries, the question of light's speed re-emerged with renewed vigour. The prevailing Aristotelian view of instantaneous light still held considerable sway, but new methods of scientific inquiry and a growing emphasis on experimentation began to challenge old dogmas. René Descartes, the influential French philosopher and mathematician, living from 1596 to 1650, also contributed to the discussion. Descartes viewed light as a pressure or tendency to move through a perfectly rigid and continuous medium that filled all space, which he called plenum. In his theory, the transmission of this pressure was instantaneous, much like how a push applied to one end of a rigid rod would immediately transmit to the other end. For Descartes, light did not travel in the sense of motion taking time. Rather, it was an immediate propagation of a state. While his concept of light's instantaneous nature aligned with Aristotle, his idea of a physical medium through which light operated foreshadowed later ideas about the ether. Descartes' influence on scientific thought was immense, and his instantaneous view of light was widely accepted among his followers. It was against this backdrop of philosophical speculation and a prevailing belief in instantaneous light that the first truly scientific attempt to measure its speed was made. This monumental effort was undertaken by Galileo Galilei, the renowned Italian polymath who lived from 1564 to 1642. Galileo is often credited with ushering in the era of modern experimental science, and his curiosity extended to the speed of a light. Galileo, unlike his predecessors, was not content with mere philosophical arguments. He believed that if light had a finite speed, however fast, it should, in principle, be measurable. His approach was pragmatic and ingenious for his time, despite its ultimate failure to yield a precise measurement. The experiment, likely conceived around 1638 and described in his posthumously published discourses and mathematical demonstrations relating to two new sciences, involved two observers with lanterns. The setup was relatively simple in concept. Galileo proposed that two individuals, each equipped with a lantern that could be quickly covered and uncovered, position themselves at a significant distance from one another. Let's imagine Galileo himself and an assistant. The first observer, Galileo, would uncover his lantern. As soon as the second observer, the assistant, saw the light from Galileo's lantern, he would immediately uncover his own lantern. The first observer would then measure the time it took from when he first uncovered his lantern until he saw the light from the assistant's lantern. The total time measured would represent the time it took for the light to travel from Galileo to the assistant, plus the time it took for the assistant to react and uncover his lantern, plus the time it took for the light to travel back from the assistant to Galileo. By conducting the experiment over different distances, Galileo hoped to isolate the time taken for light's travel. For instance, if they performed the experiment over 1 mile and then over 10 miles, the difference in the measured times, after accounting for human reaction time, would, in theory, reveal the time light took to cover the additional distance. Galileo described the experiment as follows. Let the two observers be at a distance of a few miles, say 1 or 2. Let each provide himself with a lantern so arranged that its light is covered or uncovered by the interposition of the hand. Let one of them, say A, at a given instant expose his light. The other, B, who perceives it, is to expose his own light at the very instant he sees that of A. A, in turn, is to note the instant when he sees the light of B. The interval between the instant when A exposes his light and the instant when he sees that of B, deducting the time required for B to expose his light, will give the time consumed by the light in passing to and fro over the interval between A and B. Galileo and his assistant attempted this experiment, first over short distances on land, and then reportedly over greater distances, perhaps even between 2 hills separated by several miles. They found that for any practical distance they could manage, the measured time interval was indistinguishable from what they observed when they were very close to each other. In other words, the time it took for light to travel the distance was far too short to be distinguished from the reaction time of the human observers. The human reaction time, which is typically a few tenths of a second, completely dwarfed the actual travel time of light over such distances. Galileo concluded that if the light did have a finite speed, it must be extraordinarily fast, far too rapid to be measured with the technology and methods available to him. He famously stated, "I have tried the experiment, and the result was that it was impossible to discern whether the light of the first lantern was seen at the instant of its exposure, or whether it travelled from the one place to the other with a perceptible interval of time." While he did not succeed in measuring the speed of light, his experiment was immensely significant. First, it represented a crucial shift in scientific methodology. Instead of relying on philosophical deduction or religious dogma, Galileo adopted an empirical approach, attempting to measure a physical phenomenon. This was a hallmark of the burgeoning scientific revolution. Second, his experiment, despite its negative result, did not prove that light was instantaneous. Instead, it strongly suggested that if light had a speed, it was so incredibly high that human perception and simple mechanical means could not detect the delay. This kept the question of light's finite speed alive and spurred future generations of scientists to devise more sophisticated methods. It moved the problem from the realm of philosophical speculation to that of experimental physics. The challenge of measuring such an immense speed was daunting. Even today, the speed of light is so fast that it seems instantaneous in our everyday experience. Light travels from the Sun to Earth, a distance of about 93 million miles, in approximately 8 minutes and 20 seconds. For a light signal to travel even 1 mile and back, it would take roughly 11 millionths of a second. A human reaction time is orders of magnitude slower than this. Galileo's ingenuity was in even conceiving such an experiment, given the limitations of the clock technology of his era. Accurate timekeeping devices like pendulum clocks were only just being developed around this time, and their precision was still limited. Following Galileo's pioneering, albeit inconclusive attempt, the idea that light might have a finite speed continued to gain traction among some scientists. However, definitive proof and an actual measurement would not come for several more decades. This would require observations on a cosmic scale, leveraging the vast distances of the solar system. The first successful measurement of the speed of light came from the Danish astronomer Ole Roemer in 1676. Roemer was observing the eclipses of Io, one of Jupiter's largest moons. Io orbits Jupiter, and from Earth, we can observe it periodically disappearing behind Jupiter, an eclipse, and reappearing. Roemer noticed a systematic variation in the timing of these eclipses. When Earth was moving away from Jupiter in its orbit, the eclipses appeared to be delayed. When Earth was moving towards Jupiter, the eclipses appeared to occur earlier than predicted. Roemer correctly deduced that these discrepancies were due to the finite time it took for light to travel the varying distances between Earth and Jupiter. The light had to travel an extra distance when Earth was further away, causing a delay in observation. By observing these delays over many months, Roemer calculated that it took light approximately 22 minutes to cross the diameter of Earth's orbit. While his estimate for the Earth-Sun distance, and thus the diameter of Earth's orbit, was not perfectly accurate by modern standards, and his resulting speed of light was about 25% lower than the accepted value today, his method was sound. He established, beyond reasonable doubt, that light had a finite, measurable speed. This was a monumental achievement, finally laying to rest the centuries-old philosophical debate. It proved that light was not an instantaneous phenomenon, but something that travelled across space and took time to do so. Following Roemer's breakthrough, other scientists would devise increasingly precise methods to measure light's speed, using both astronomical and terrestrial approaches. These future experiments, building on the foundation laid by Galileo's conceptual attempt and Roemer's initial success, would refine our understanding of this fundamental constant of the universe. The early ideas, from ancient philosophical musings to Galileo's practical experiment, were essential steps in shifting human understanding of light from an abstract quality to a measurable, physical phenomenon, paving the way for the profound discoveries of later centuries. The evolution of thought from ancient times concerning light was a gradual process, moving from highly speculative philosophical positions to more empirical and quantitative ones. The challenge was immense because light's speed is so great that it defies everyday human experience. For most of human history, the idea of light travelling at a finite speed seemed counterintuitive. If you lit a candle, the room appeared to be illuminated immediately. There was no perceptible delay. This everyday observation strongly supported the Aristotelian view of instantaneous illumination. However, as observational tools improved and as scientific methodology became more rigorous, particularly during the scientific revolution, the instantaneous view began to face scrutiny. Galileo's attempt, while unsuccessful in measurement, was crucial because it introduced the idea that a natural phenomenon, even one as fleeting as light, could be subjected to experimental verification. It planted the seed that the answer lay not in philosophical debate, but in careful observation and measurement. The failure of his experiment, therefore, was not a failure of the hypothesis, but a testament to the immense speed of light and the limitations of the available technology. The conceptual shift from instantaneous to finite speed was not merely an academic exercise. It had profound implications for how the universe was understood. If light had a speed, it meant that when we looked at distant stars, we were seeing them not as they are now, but as they were when the light left them. This idea, which is commonplace today, was revolutionary. It introduced the concept of looking back in time by observing the cosmos, an idea that would later become central to astronomy and cosmology. The early work on light, though often primitive by modern standards, created the intellectual scaffolding upon which future theories and experiments would be built. From the initial philosophical debates of the Greeks to the empirical attempts of Galileo and the astronomical observations of Roemer, each step contributed to a clearer, more precise understanding of light's nature. This progression from pure thought to attempted measurement, even if initially frustrating, underscored a fundamental principle of science, that even the most seemingly instantaneous phenomena might, upon closer inspection and with better tools, reveal a finite, measurable quality. The journey to understand why light has a speed limit truly began with these foundational questions and the tireless efforts of early thinkers to answer them. The simplicity of the question belied the complexity of the phenomenon and the experimental challenges it posed for centuries. The conceptual leap from light as an immediate presence to light as a travelling entity was one of the first major breakthroughs in understanding its fundamental properties. The nature of light has been a subject of intense scientific debate for centuries. Is light a stream of tiny particles, or does it behave like a wave, similar to ripples on water or sound travelling through air? This question, seemingly straightforward, led to a long-standing scientific controversy that spanned from the 17th century well into the 20th century, ultimately revealing a deeper, more complex reality. The arguments for each view were compelling, supported by observations and experiments that, at different times, seemed to favour one over the other. In the 17th century, two prominent theories emerged to explain the behaviour of light: the corpuscular theory and the wave theory. Leading the charge for the particle view was the towering figure of Isaac Newton, the English physicist and mathematician who lived from 1642 to 1727. Newton, whose work fundamentally reshaped physics with his laws of motion and universal gravitation, proposed that light consisted of a stream of extremely small discrete particles, which he called corpuscles. Newton's corpuscular theory explained several observed phenomena very elegantly. For instance, the phenomenon of reflection, where light bounces off a surface, could be easily understood. If light was made of particles, then when these particles struck a smooth surface, they would bounce off in a predictable manner, much like tiny billiard balls. The angle at which they hit the surface would be equal to the angle at which they bounced off, perfectly consistent with the law of reflection. Refraction, the bending of light as it passes from one medium to another, for example, from air into water, was also explained by Newton's theory. He proposed that when light corpuscles entered a denser medium, they experienced a force that pulled them towards the normal, an imaginary line perpendicular to the surface. This force would cause the particles to accelerate, meaning they would travel faster in the denser medium. Therefore, according to Newton's corpuscular theory, light should travel faster in water or glass than in air. This specific prediction would later become a crucial test between the wave and particle theories. Another strong point in favour of the corpuscular theory was its ability to explain the formation of sharp shadows. If light travelled as distinct particles in straight lines, then when these particles were blocked by an opaque object, they would cast a clear, sharp shadow with a distinct boundary between light and dark. This was precisely what was observed in everyday life. The concept of light travelling in straight lines, known as rectilinear propagation, was a natural consequence of the particle view. Newton's immense scientific authority and the success of his other theories meant that his corpuscular theory of light gained widespread acceptance, particularly in England, and dominated scientific thought throughout the 18th century. His detailed studies of prisms, demonstrating how white light could be split into a spectrum of colours and then recombined, also fit well with his particle view, suggesting that different colours were associated with different types or sizes of corpuscles. However, at roughly the same time Newton was developing his corpuscular theory, a competing idea was being proposed by Christian Huygens, a Dutch physicist, astronomer and mathematician who lived from 1629 to 1695. Huygens advocated for a wave theory of light. He proposed that light was not a stream of particles, but rather a series of waves or vibrations that propagated through an invisible, elastic medium that filled all space, which he called the luminiferous ether. Huygens' wave theory was based on his principle, now known as Huygens' principle. This principle states that every point on a wavefront, the leading edge of a propagating wave, can be considered as a source of new spherical wavelets. These wavelets expand outward, and the new wavefront is formed by the envelope of all these secondary wavelets. This principle allowed Huygens to explain reflection and refraction from a wave perspective. For reflection, Huygens showed that if waves struck a surface, the secondary wavelets would combine to form a reflected wavefront, obeying the law of reflection. For refraction, his wave theory predicted something different from Newton's particle theory. When a light wave entered a denser medium, like water, Huygens argued that the wave's speed would decrease. The change in speed would cause the wavefront to bend, leading to refraction. This was a direct contradiction to Newton's prediction that light would speed up in a denser medium. This difference in prediction concerning the speed of light in different media would later become a decisive experimental test. Huygens' wave theory also provided a natural explanation for phenomena like diffraction, where light seemed to bend around obstacles or spread out after passing through small openings. While Newton's particle theory struggled to explain why light didn't always cast perfectly sharp shadows and sometimes showed slight spreading, the wave theory could account for this bending behaviour, similar to how water waves spread out after passing through a gap. However, the evidence for diffraction was not as clear-cut in the 17th century, and the effects were often subtle, making the particle explanation of sharp shadows seem more convincing to many. The primary challenge for Huygens' wave theory was the concept of the ether. If light was a wave, what was it waving in? Sound waves need air or another medium to travel. Water waves need water. If light travelled through the vacuum of space, then the ether had to be present everywhere, including within what seemed to be empty space. Describing the properties of this invisible, undetectable medium that could transmit light waves at such high speeds became a significant hurdle for the wave theory. Furthermore, the wave theory struggled to explain why light seemed to travel in straight lines and cast sharp shadows, given that waves tend to spread out more. Throughout the 18th century, Newton's colossal reputation meant that his corpuscular theory largely overshadowed Huygens' wave theory, particularly in England. Scientists continued to refine optical instruments based on the principles of light travelling in straight lines and behaving like particles. The wave theory, despite its elegant explanations for some phenomena, remained a minority view. However, the tide began to turn dramatically in the early years of the 19th century, thanks largely to the work of a brilliant English polymath named Thomas Young, who lived from 1773 to 1829. Young, a physician, physicist, and linguist, provided compelling experimental evidence that strongly supported the wave nature of light. Young's most famous experiment, often called the double-slit experiment, provided irrefutable evidence of light's wave-like behaviour. In 1801, Young devised an experiment where he allowed a beam of light to pass through two very narrow, closely spaced slits. If light were made of particles, he reasoned, these particles would simply pass through the slits and create two bright lines on a screen behind them, corresponding to the two slits. However, what Young observed was entirely different. Instead of two bright lines, he saw a pattern of alternating bright and dark bands or fringes. This interference pattern was a hallmark of wave behaviour. When two waves meet, they can either reinforce each other, constructive interference, leading to a brighter region, or cancel each other out, destructive interference, leading to a dark region. This is precisely what happens with water waves or sound waves. Young's experiment demonstrated that light waves, after passing through the two slits, interfered with each other, producing the observed pattern of bright and dark fringes. This phenomenon was impossible to explain with particles travelling in straight lines. The experiment provided strong evidence that light was indeed a wave. Young also worked on the phenomenon of diffraction, further demonstrating how light could bend around corners or spread out after passing through small apertures, producing patterns that could only be explained by the wave nature of light. His work, along with his explanation of colour perception based on three primary colours, significantly revived the wave theory. Around the same time, independently and with powerful mathematical rigour, the French engineer and physicist Augustin Jean Fresnel, who lived from 1788 to 1827, also developed a comprehensive wave theory of light. Fresnel's work was particularly strong in explaining diffraction and interference patterns with mathematical precision. He refined Huygens' principle, providing a more robust mathematical framework for how waves propagate and interfere. One of the most striking confirmations of Fresnel's wave theory came from an unexpected source. Siméon Poisson, a French mathematician who was initially a critic of Fresnel's wave theory, deduced a seemingly absurd prediction from Fresnel's equations. Poisson calculated that if a perfectly opaque circular obstacle was illuminated by a point source of light, then according to the wave theory, there should be a tiny bright spot precisely at the centre of the shadow cast by the obstacle. This prediction, derived purely from mathematical theory, seemed counterintuitive for a phenomenon traditionally associated with sharp shadows. However, in 1818, François Arago, another French physicist, performed the experiment and indeed observed the bright spot, which came to be known as the Poisson spot, or Arago spot. This striking experimental confirmation provided powerful evidence in favour of Fresnel's wave theory and against the simple particle view. Another important phenomenon that strongly supported the wave theory was polarization. Light can be polarized, meaning its vibrations occur in a specific plane. For example, when light passes through certain crystals, it can be split into two beams, each polarized in a different direction. This behavior was difficult to explain with simple, spherical particles. However, if light was a transverse wave, meaning its oscillations are perpendicular to the direction of propagation, like waves on a string, then the different planes of vibration could easily account for polarization. This distinction between longitudinal waves, like sound, where oscillations are parallel to propagation, and transverse waves became crucial in the development of the wave theory. Thomas Young was among the first to suggest that light waves must be transverse. By the mid-19th century, The experimental evidence in favour of the wave theory had become overwhelming. Young's interference experiments, Fresnel's detailed mathematical framework, the confirmation of the Poisson spot, and the elegant explanation of polarization all pointed strongly towards light behaving as a wave. The final nail in the coffin for Newton's idea that light travels faster in denser media came from Hippolyte Fizeau and Léon Foucault, French physicists. Fizeau, in 1850, performed an experiment that compared the speed of light in air and water. He used a rotating toothed wheel to chop a beam of light, sending it over a long distance and back. Foucault, in 1862, refined this method using rotating mirrors. Their experiments definitively showed that light travels slower in water than in air. This direct experimental result perfectly matchuyst the prediction of Huygens' wave theory and directly contradicted Newton's particle theory. This was a decisive victory for the wave model. With the success of the wave theory, the scientific community largely accepted that light was a wave. The focus then shifted to understanding the nature of the ether through which these waves were supposedly propagating. If light was an electromagnetic wave, as Maxwell would later show, and it needed a medium, then the ether had to possess very specific and increasingly problematic properties. It had to be rigid enough to support very high-frequency vibrations, the waves of light, and therefore very high speeds, yet it also had to be tenuous and invisible enough to offer no resistance to planets moving through it. This conceptual difficulty would set the stage for the next great revolution in physics. Despite the strong evidence for the wave theory, the story of light's nature was not yet complete. Certain phenomena, particularly those involving the interaction of light with matter at the atomic level, would later prove difficult to explain solely with a wave model. The photoelectric effect, for example, where light causes electrons to be ejected from a metal surface, could not be adequately explained by the wave theory. This phenomenon suggested that light also behaved as if it were made of discrete packets of energy. This would eventually lead to the concept of wave-particle duality, proposed in the 20th century, which states that light exhibits properties of both waves and particles, depending on how it is observed or interacted with. The historical debate between the wave and particle theories of light was a classic example of scientific progress. It was not a simple case of one theory being entirely right and the other entirely wrong. Both theories had strengths in explaining certain aspects of light's behaviour. Newton's particle theory offered intuitive explanations for reflection and sharp shadows, and held sway for a long time due to his authority. However, as new experimental techniques emerged, and phenomena like interference, diffraction, and polarization were meticulously studied, the wave theory provided more consistent and comprehensive explanations. The decisive experimental results, particularly those related to interference patterns and the speed of light in different media, ultimately tipped the scales in favour of the wave model in the 19th century. This intellectual journey highlighted the critical role of experimental evidence in resolving scientific controversies and pushing the boundaries of human understanding. The debate set the stage for later breakthroughs that would reveal the true, dual nature of light. The journey to accurately measure the speed of light is a testament to human ingenuity and the relentless pursuit of precision in science. For centuries it was believed by many, including influential thinkers like Aristotle and Descartes, that light propagated instantaneously across any distance. However, as scientific methods evolved, a different view began to take hold. The idea that light, like everything else, possessed a finite speed, however incredibly fast. The challenge then became not just to theorize this, but to prove it through observable phenomena and precise measurements. The story of measuring light's speed is a narrative of improving technology, clever experimental design, and the slow but sure convergence on a universally accepted value. The very first compelling evidence that light had a finite speed, rather than being instantaneous, came from the realm of astronomy in the late 17th century. This groundbreaking discovery was made by the Danish astronomer Ole Roemer, who lived from 1644 to 1710. Roemer was working at the Paris Observatory, where he was meticulously observing the moons of Jupiter. Specifically, he focused on Io, the innermost of Jupiter's 4 largest moons. which was known for its relatively quick orbital period and frequent eclipses. An eclipse occurred when Io passed behind Jupiter, disappearing from Earth's view and then reappeared. These events were predictable based on Io's known orbit around Jupiter. Roemer, along with his supervisor Giovanni Domenico Cassini, had compiled extensive tables predicting the times of Io's eclipses. However, as they continued their observations over many months, Roemer noticed a peculiar and systematic pattern in the timing of these eclipses. He observed that the predicted times of Io's reappearances from behind Jupiter were not always accurate. When Earth was moving away from Jupiter in its orbit around the Sun, the eclipses seemed to occur later than predicted. Conversely, when Earth was moving towards Jupiter, the eclipses seemed to occur earlier than predicted. The maximum delay or advance in timing that Roemer observed was about 11 minutes when Earth moved from its closest point to Jupiter to its furthest point from Jupiter. Roemer correctly deduced that these variations could only be explained if light took a finite amount of time to travel the changing distance between Earth and Jupiter. As Earth moved further away from Jupiter, the light from Io's reappearance had to travel a greater distance to reach Earth, causing a delay in its observation. When Earth moved closer, the distance light had to travel decreased, causing the eclipses to appear earlier. He reasoned that the accumulated delay over several months, as Earth moved from its position closest to Jupiter to its position farthest from Jupiter, was due to the extra distance light had to cover across Earth's orbit. In a presentation to the French Academy of Sciences in 1676, Roemer explained his findings. He calculated that light took approximately 22 minutes to cross the diameter of Earth's orbit. At that time, the exact diameter of Earth's orbit was not known with high precision. Based on his 22-minute estimate and the best available estimates for the size of Earth's orbit, Roemer calculated the speed of light to be roughly 210,000 kilometers per second, or about 130,000 miles per second. This was a remarkable achievement. While his value was about 25% lower than the currently accepted speed, his method was sound, and his discovery provided the first definitive experimental proof that light travels at a finite speed, ending centuries of speculation. It opened up a whole new area of scientific inquiry. Despite Roemer's compelling evidence, his discovery was not immediately and universally accepted. Some prominent scientists, including his former mentor Cassini, remained skeptical, preferring to attribute the observed discrepancies to irregularities in Io's orbit rather than the finite speed of light. However, over time, as further astronomical observations confirmed the pattern Roemer had identified, his explanation gained wider acceptance. James Bradley, an English astronomer, further solidified the idea in 1728 through his discovery of stellar aberration, which was another astronomical phenomenon that could only be explained by light having a finite speed and Earth moving through space. For nearly 2 centuries after Roemer, efforts to measure the speed of light shifted from astronomical observations to terrestrial experiments. The goal was to conduct measurements entirely on Earth, providing a more controlled environment and potentially greater precision. This was a significant challenge because, even over distances achievable on Earth, light travels incredibly fast, making the time intervals extremely short and difficult to measure with the available technology. Precise clocks, optical instruments, and clever experimental setups were needed. The first successful terrestrial measurement of the speed of light was performed by the French physicist Hippolyte Fizeau, who lived from 1819 to 1896. Fizeau's experiment, conducted in 1849, was a landmark achievement. It was the first time the speed of light was measured without relying on astronomical distances. Fizeau's setup was ingenious. He used a rapidly rotating toothed wheel, much like a gear with many teeth and gaps. A beam of light was shone through one of the gaps in the wheel. After passing through the gap, the light travelled a significant distance, reflected off a mirror, and then returned along the same path. The crucial part of the experiment was that this returning light had to pass back through the same gap in the rotating wheel to be observed by Fizeau. The experiment worked like this. A light source was positioned so that its beam passed through a gap between 2 teeth of the rotating wheel. The light then travelled about 8,633 metres, about 5.36 miles, to a distant mirror. The mirror reflected the light back towards the rotating wheel. If the wheel was rotating at a certain speed, by the time the light returned, the gap it had originally passed through might have moved on, and a tooth might now be in its place, blocking the light from reaching the observer. However, if the wheel rotated at a specific faster speed, the next gap would precisely align with the returning light, allowing it to pass through to the observer. By slowly increasing the rotation speed of the wheel, Fizeau could observe when the returning light was first blocked, by a tooth moving into the path of the original gap, then when it reappeared, when the next gap aligned, then when it was blocked again, and so on. By measuring the speed of the wheel's rotation at which the light was blocked or reappeared, and knowing the number of teeth on the wheel, Fizeau could calculate the time it took for the light to travel to the mirror and back. Knowing the total distance travelled, twice the distance to the mirror, he could then calculate the speed of light. Fizeau's toothed wheel had 720 teeth. He found that at a rotation speed of approximately 12.6 revolutions per second, the returning light was completely blocked by a tooth. At twice that speed, or about 25.2 revolutions per second, the light reappeared, meaning the next gap had moved into position. Using these measurements, Fizeau calculated the speed of light to be 315,000 kilometers per second, 195,728 miles per second. This was very close to the modern accepted value, and significantly more accurate than Roemer's astronomical measurement. Fizeau's experiment was a triumph of terrestrial measurement, showing that the speed of light could be determined with precision on Earth. Just a few years after Fizeau, another French physicist, Léon Foucault, who lived from 1819 to 1868, developed an even more precise method for measuring the speed of light. Foucault's experiment, performed in 1862, utilized a rapidly rotating mirror instead of a toothed wheel. This method was technically more challenging but offered greater accuracy. In Foucault's setup, a beam of light from a source was directed to a rapidly rotating mirror. As the mirror spun, it reflected the light beam towards a stationary mirror located a considerable distance away. After reflecting off the stationary mirror, the light travelled back to the rotating mirror. During the time it took for the light to travel to the stationary mirror and back, the rotating mirror would have spun through a small angle. Because the mirror had rotated, the returning light beam would be reflected at a slightly different angle compared to the initial outbound beam. This slight deflection of the returning beam was then measured. By precisely measuring the angle of deflection of the returning light, and knowing the speed of the mirror's rotation and the distance to the stationary mirror, Foucault could calculate the time it took for the light to make the round trip. From this time and the known distance, he could determine the speed of light. Foucault's experiment yielded a value of 298,000 kilometers per second, 185,177 miles per second. This result was even closer to the modern accepted value than Fizeau's. Foucault's method had another profound impact beyond just providing a more accurate measurement. He also used his apparatus to compare the speed of light in air and in water. His experiments unequivocally demonstrated that light travels slower in water than it does in air. This finding was extremely significant because it directly contradicted Isaac Newton's corpuscular, particle theory of light, which predicted that light particles should speed up in a denser medium like water. Conversely, Foucault's results strongly supported Christian Huygens' wave theory of light, which predicted that light waves would slow down when entering a denser medium. Foucault's experiment thus provided crucial evidence that solidified the wave theory of light as the dominant paradigm in the 19th century. Towards the end of the 19th century, and into the early 20th century, the American physicist Albert Abraham Michelson, who lived from 1852 to 1931, dedicated much of his career to achieving even greater precision in measuring the speed of light. Michelson's work was meticulous and groundbreaking, and he became renowned for his highly accurate measurements. Michelson initially refined Foucault's rotating mirror method. In 1879, he conducted experiments at the United States Naval Academy in Annapolis, Maryland, using an improved version of Foucault's apparatus. He placed the distant mirror approximately 600 meters, about 2,000 feet, away. His measurements yielded a value of 299,910 kilometers per second, 186,377 miles per second. This was the most accurate measurement to date. Michelson continued his work, collaborating with Edward Morley, a chemist, in a series of famous experiments, most notably the Michelson-Morley experiment of 1887. While this particular experiment's primary goal was to detect the luminiferous ether, which will be discussed in the next chapter, its precision in optical measurement was unparalleled for its time. Michelson's continued efforts to refine the speed of light measurement led to even greater accuracy. In the 1920s, Michelson undertook his most ambitious measurements. He conducted experiments over very long distances, using large rotating mirrors and precise timing equipment. One of his most famous experiments involved measuring the speed of light between two mountain peaks in California, Mount Wilson and Mount San Antonio, also known as Mount Baldy. The distance between these two peaks was approximately 35 kilometers, about 22 miles. He used a powerful light source and a system of rapidly spinning octagonal mirrors with 8 sides. The light would travel from Mount Wilson to a mirror on Mount San Antonio and reflect back to Mount Wilson, where it would strike the rotating octagonal mirror again. By precisely adjusting the rotation speed of the octagonal mirror until the returning light beam was perfectly reflected to the observer, Michelson could calculate the time of travel and thus the speed of light. He used vacuum tubes over a portion of the path to minimize the effects of air, further enhancing accuracy. His measurements from 1926 gave a value of 299,796 kilometers per second, 186,284 miles per second. Michelson continued to strive for even greater precision, conducting experiments in a long vacuum tube at the Irvine Ranch near Santa Ana, California, during the 1930s. This final set of experiments, interrupted by his death in 1931 and completed by his colleagues, aimed to eliminate the effects of atmospheric variations on the light path. These later measurements, along with others performed by different scientists around the world using various techniques, such as Kerr cells and electronic methods, consistently converged on a highly precise value. By the mid-20th century, with the advent of radar and microwave technology, new methods for measuring the speed of electromagnetic waves, of which light is a part, emerged, offering even greater accuracy. These methods, often relying on the precise measurement of frequencies and wavelengths, further refined the value of C. The pursuit of the speed of light culminated in 1975, when the International Bureau of Weights and Measures formally adopted a value for the speed of light in a vacuum, 299,792,458 meters per second. This value was so precise that in 1983, the meter itself was redefined in terms of the speed of light. The meter is now defined as the distance light travels in 1,299,792,458th of a second. This means that the speed of light in a vacuum is now a defined constant, not something that needs to be measured repeatedly. Instead, measuring the speed of light is equivalent to measuring the length of the meter. The 19th century was a period of immense scientific progress, particularly in the understanding of electricity, magnetism, and light. As scientists began to grasp that light exhibited wave-like properties, a fundamental question arose. If light is a wave, what is it waving in? Just as sound waves require a medium like air or water to travel, and water waves require water, it seemed logical that light waves too must propagate through some kind of substance. This led to the widespread adoption of the concept of the luminiferous ether. The luminiferous ether, often simply called the ether, was a hypothetical medium proposed to fill all of space. Its primary purpose was to provide a physical medium for the propagation of light waves. For many scientists of the time, the idea of waves traveling through an absolute vacuum seemed counterintuitive, even impossible. Waves, by definition, were disturbances in a medium. Without a medium, how could light waves exist or travel across the vast emptiness between stars and planets? The concept of an ether was not entirely new. As far back as ancient Greek philosophy, thinkers like Aristotle had proposed the existence of an ether as a fifth element, a pure, unchanging substance that filled the heavens and was distinct from the four earthly elements. In the 17th century, René Descartes, while believing light was instantaneous, imagined a plenum, or subtle fluid filling space that transmitted light as a pressure. Isaac Newton also toyed with the idea of a subtle ether, though he did not firmly commit to it for light propagation. However, the luminiferous ether of the 19th century was a much more specific and physically defined entity, necessitated by the growing evidence for light's wave nature. The early 19th century, particularly with the work of Thomas Young and Augustin Jean Fresnel, provided strong experimental support for the wave theory of light. Young's double-slit experiment clearly demonstrated interference patterns, a hallmark of wave behaviour. Fresnel's mathematical descriptions of diffraction and interference further solidified the wave model. If light was indeed a wave, then the ether became a crucial component of the physical picture. Scientists began to attribute very specific properties to this hypothetical ether to explain light's observed characteristics. First, for light to travel at such an incredibly high speed, the ether had to be extremely rigid or stiff, like a solid, yet also perfectly elastic. A very rigid medium would allow for rapid transmission of vibrations. Second, the ether had to be incredibly tenuous and massless, offering no resistance to the motion of celestial bodies. Planets and stars moved freely through space for billions of years without any noticeable drag. If the ether were dense or viscous, it would slow them down, which was clearly not observed. Third, it had to be completely transparent and undetectable by any means other than the propagation of light itself. It filled everything, yet it was invisible and insensible. The properties required of the ether were therefore quite contradictory. It had to be a rigid solid to transmit transverse waves. Light waves were understood to be transverse, vibrating perpendicular to their direction of travel, at enormous speeds, but also completely frictionless and massless to allow objects to move through it unimpeded. This paradox began to pose significant theoretical challenges as the 19th century progressed. One of the central assumptions of the ether theory was that the ether provided an absolute reference frame for light. This meant that the speed of light, denoted as c, would only be c when measured relative to the stationary ether. If an observer or a light source was moving through the ether, then the measured speed of light would appear different, either faster or slower, depending on the observer's motion relative to this stationary ether. This was analogous to sound waves. The speed of sound is constant relative to the air, but if you measure the speed of sound from a moving car, it will appear different depending on your motion relative to the air. This concept led to the idea that it should be possible to detect Earth's motion through the ether. Earth orbits the Sun at a speed of approximately 30 kilometers per second, about 18.6 miles per second. If the ether was stationary, then as Earth moved through it, there should be an ether wind blowing past Earth, similar to how a moving car experiences a wind even on a calm day. This ether wind should affect the measured speed of light depending on the direction of measurement. For example, light travelling in the direction of Earth's motion through the ether should appear slower, while light travelling against the ether wind should appear faster. This theoretical prediction spurred several experimental attempts to detect the ether wind. The most famous and meticulously performed of these experiments was conducted by Albert Abraham Michelson, an American physicist, and Edward Morley, an American chemist and physicist, in 1887. Their collaboration in Cleveland, Ohio, aimed to directly detect the relative motion of Earth through the luminiferous ether. The Michelson-Morley experiment was designed with extraordinary precision. It utilized an interferometer, a device Michelson had invented, which could detect extremely tiny differences in the speed of light over different paths. The core idea of the interferometer was to split a single beam of light into two beams that travelled along different paths, then recombine them. If the speed of light changed along one path due to the ether wind, it would cause a phase difference between the two recombined beams, resulting in an observable interference pattern, alternating bright and dark fringes that would shift as the apparatus was rotated. The interferometer was set up on a massive stone slab, floating in a pool of mercury. This allowed the entire apparatus to be rotated smoothly and precisely, so that the two light paths could be oriented in different directions relative to Earth's presumed motion through the ether. One arm of the interferometer would be aligned parallel to Earth's motion and the other perpendicular to it. According to the ether theory, light travelling along the parallel arm would be affected by the ether wind, experiencing a slight delay in its round trip compared to light travelling along the perpendicular arm. This difference in travel time, though extremely small, was calculated to be detectable by their sensitive instrument. Michelson and Morley carefully performed their experiment, rotating the apparatus and making observations over many hours and at different times of the year, to account for Earth's changing direction of the motion in its orbit. To their astonishment, and to the astonishment of the scientific community, they found no detectable shift in the interference pattern. Regardless of the orientation of the apparatus or the time of year, the speed of light appeared to be the same in all directions. The result of the Michelson-Morley experiment was a profound puzzle. It implied that there was no ether wind, and therefore no stationary ether through which Earth was moving. The experiment's null result directly contradicted the prevailing ether theory, and the idea that the speed of light should vary depending on the observer's motion relative to a fixed medium. It was one of the most significant negative results in the history of science, leading to a crisis in physics. Various attempts were made to explain away the null result while preserving the ether concept. One famous proposal came from George Fitzgerald, an Irish physicist, and Hendrik Lorentz, a Dutch physicist. They independently suggested that objects moving through the ether would physically contract in the direction of their motion, and that clocks would slow down, in just such a way as to precisely cancel out the expected effect of the ether wind on light speed. This Lorentz-Fitzgerald contraction was an attempt to save the ether theory by introducing new, unproven physical effects. While these mathematical transformations, now known as the Lorentz transformations, would later become fundamental to special relativity, their original motivation was to preserve the ether. Another idea was that the ether was somehow dragged along by moving objects, so that Earth carried its own local pocket of ether, meaning there would be no relative motion to detect. However, this ether drag hypothesis was contradicted by other astronomical observations, such as stellar aberration, which required light to come from distant stars through an ether that was not dragged by Earth. The Michelson-Morley experiment's failure to detect the ether wind gradually led many physicists to question the very existence of the luminiferous ether. The properties required for the ether were becoming increasingly contradictory and complex, stretching the limits of believability. It needed to be a perfect fluid for celestial motion, but a perfectly rigid solid for wave propagation. It had to be ubiquitous yet undetectable. The elegant simplicity of light travelling without a medium began to seem more plausible than the increasingly contrived properties of the ether. The definitive solution to the ether problem came with Albert Einstein's special theory of relativity, published in 1905. Einstein's theory completely discarded the concept of the luminiferous ether. Instead, he based his theory on two fundamental postulates. The first postulate stated that the laws of physics are the same for all observers in uniform motion, inertial frames of reference. The second and revolutionary postulate stated that the speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. Einstein's second postulate directly explained the null result of the Michelson-Morley experiment without needing any ether or ad hoc contractions. If the speed of light is truly constant for everyone, no matter how fast they are moving, then there is no need for a special medium or a preferred reference frame. The ether, having no observable effect and leading to theoretical contradictions, became unnecessary. Einstein's theory provided a simpler, more elegant explanation for why the speed of light appears constant. The abandonment of the ether concept was a profound paradigm shift in physics. It meant that light, unlike other waves familiar at the time, did not require a medium to propagate. It was an electromagnetic phenomenon that could travel through the emptiness of space by virtue of oscillating electric and magnetic fields. This was a radical departure from classical physics, which always sought a mechanical explanation or a medium for wave propagation. The demise of the ether had far-reaching consequences. It cleared the way for a deeper understanding of the fundamental nature of space and time themselves. Without a preferred ether frame, all inertial reference frames became equivalent, leading to the mind-bending consequences of special relativity, such as time dilation, time slowing down for moving objects, and length contraction, objects appearing shorter in the direction of a motion, which were no longer seen as physical changes to objects but as consequences of the very nature of space-time. The late 19th century was a period of intense scientific inquiry, particularly concerning the nature of light and the medium through which it was believed to travel. By this time, the wave theory of light had largely triumphed over the particle theory, primarily due to compelling experimental evidence such as Young's interference patterns and Foucault's measurements showing light travels slower in water than in air. With light firmly established as a wave, the prevailing scientific consensus held that, like all other known waves, light must propagate through some kind of medium. This hypothetical, invisible and all-pervading substance was termed the luminiferous ether. The luminiferous ether was envisioned as the universal medium for light waves. Scientists believed it filled all of space, permeating even the vacuum, and provided the necessary substrate for light to travel from the Sun to the Earth and across vast interstellar distances. A key assumption of the ether theory was that this medium was stationary, providing an absolute reference frame for the universe. This meant that the speed of light, measured relative to this stationary ether, would always be a constant value. However, if an observer, like Earth, was moving through this stationary ether, then the measured speed of light should appear different, depending on the direction of Earth's motion relative to the ether. This expected variation in light speed due to Earth's movement through the ether was referred to as the ether wind. The Earth orbits the Sun at a considerable speed, approximately 30 kilometers per second, or about 18.6 miles per second. If the ether was indeed stationary, then as Earth moved through it, there should be a detectable ether wind blowing past Earth. This would be analogous to a boat moving through water. Even if the water itself is still, the moving boat experiences a flow of water relative to it. Detecting this ether wind became a major scientific goal, as it would provide direct evidence for the existence of the ether and confirm its role as the universal medium for light. Among the scientists eager to detect this elusive ether wind was Albert Abraham Michelson, an American physicist who lived from 1852 to 1931. Michelson was an expert in optics and interferometry, the science of using interference patterns of light waves to make precise measurements. In 1881, while working in Germany, Michelson designed and built an apparatus specifically for detecting the ether wind. This initial experiment, though innovative, suffered from some limitations in sensitivity. It suggested no significant ether wind, but Michelson himself concluded that its precision was not high enough to definitively rule out the effect. Michelson returned to the United States and, in 1887, collaborated with Edward Morley, an American chemist and physicist, who lived from 1838 to 1923 at the Case School of Applied Science in Cleveland, Ohio. Together, they designed and conducted a much more sensitive and refined version of the experiment, which became famously known as the Michelson-Morley experiment. Their goal was clear: to precisely measure the tiny variations in the speed of light that would be caused by Earth's motion through the stationary luminiferous ether. The core of their experimental setup was a device called an interferometer. Michelson's interferometer worked on the principle of splitting a single beam of light into two separate beams, sending them along different paths, and then recombining them. If the two beams travelled at slightly different speeds, or if one path experienced a greater delay than the other, it would cause the waves to be out of phase when they recombined. This phase difference would manifest as a shift in the interference pattern observed through a telescope. An interference pattern is a series of alternating bright and dark lines or fringes, created when two light waves either reinforce each other, bright fringes, or cancel each other out, dark fringes. Here is a simplified description of the Michelson-Morley interferometer. A single beam of light from a powerful source was directed towards a semi-silvered mirror, also called a beam splitter. This mirror was designed to transmit about half of the light and reflect the other half. The reflected part of the beam travelled along one arm of the interferometer to a fully silvered mirror, mirror 1, at a certain distance, then reflected back to the beam splitter. The transmitted part of the beam travelled along a perpendicular arm to another fully silvered mirror, mirror 2, at an equal distance, then also reflected back to the beam splitter. When both reflected beams returned to the beam splitter, they were recombined and directed towards a telescope where the interference pattern was observed. The genius of the setup lay in its sensitivity to relative changes in the speed of light. If Earth was moving through the ether, then the speed of light along the arm parallel to Earth's motion would be affected by the ether wind. Light travelling against the wind would be slowed down, and light travelling with the wind would be sped up. The round-trip time for this parallel arm would be slightly longer than if there were no ether wind. In contrast, light travelling along the perpendicular arm would be less affected by the ether wind, or affected in a different, typically smaller way. This small difference in travel time between the two arms, caused by the hypothetical ether wind, would result in a detectable shift in the interference fringes when the apparatus was rotated. To maximise the sensitivity and ensure that even a tiny effect could be detected, Michelson and Morley took extraordinary measures in their experimental design. First, they extended the effective length of the light paths by using multiple reflections. Each arm of the interferometer was designed with several mirrors, causing the light to bounce back and forth multiple times within each arm, effectively increasing the path length from about 11 metres, about 36 feet, to 65 metres, about 213 feet. This magnified any potential time difference. Second, to eliminate vibrations and temperature changes that could affect the delicate measurements, the entire optical apparatus was mounted on a massive stone slab. This slab measured about 1.5 metres, about 5 feet, square and 45 centimetres, about 18 inches, thick. Third, this heavy stone slab was floated in a trough of liquid mercury. This allowed the entire apparatus to be rotated smoothly and continuously, without introducing vibrations or distortions. The mercury bath provided a nearly frictionless bearing, enabling the researchers to rotate the interferometer slowly and observe any shifts in the fringe pattern as its orientation to the presumed ether wind changed. The experiment was carried out over several days and nights in July 1887. Michelson and Morley repeatedly rotated the interferometer through a full 360 degrees, observing the interference fringes through the telescope. According to the ether theory, they expected to see a measurable shift in the interference pattern as the arms aligned with and against the direction of Earth's motion through the ether. The predicted shift was small, but well within the capabilities of their highly sensitive instrument. To their profound surprise, and to the astonishment of the scientific world, Michelson and Morley observed no significant shift in the interference fringes, regardless of the orientation of the apparatus or the time of year, which would change Earth's direction relative to any fixed ether. The speed of light appeared to be the same in all directions. There was no detectable ether wind. The result was a null result. The expected effect was simply not there. The significance of this null result was immense. It directly contradicted the prevailing ether theory, which had been the cornerstone of light propagation for decades. If the ether existed and was stationary, the effect should have been observed. The failure to detect an ether wind meant that either the ether did not exist, or it possessed properties so bizarre as to make it undetectable, or light itself behaved in a fundamentally different way than previously imagined. The Michelson-Morley experiment created a major crisis in physics. Scientists grappled with various explanations to reconcile the null result with the assumed existence of the ether. One hypothesis was ether drag, suggesting that Earth somehow dragged the surrounding ether along with it. However, this was contradicted by astronomical observations like stellar aberration, which showed that starlight, when entering Earth's atmosphere, behaves as if it's coming from a source whose apparent position shifts due to Earth's motion, implying the ether is not dragged along by Earth. Another, more famous attempt to explain the null result while preserving the ether came from George Fitzgerald, an Irish physicist, and Hendrik Lorentz, a Dutch physicist. They independently proposed that objects moving through the ether would physically contract in the direction of their motion, and that clocks would slow down in precisely the right amounts to cancel out the expected effect of the ether wind. This Lorentz-Fitzgerald contraction was a clever mathematical fix to make the ether theory consistent with the experimental result. However, it seemed rather ad hoc, lacking a deeper physical explanation for why objects should contract or clocks should slow down when moving through this unseen medium. Despite these attempts, the ether theory began to crumble under the weight of the Michelson-Morley experiment's findings. The properties required for the ether became increasingly contradictory. It had to be a rigid solid to support transverse light waves at incredibly high speeds, yet completely frictionless and massless to allow planets to move through it without resistance. The idea of a medium that was everywhere and affected everything, yet was utterly undetectable, became less and less tenable. The true resolution to the ether puzzle came in 1905 with Albert Einstein's special theory of relativity. Einstein, who lived from 1879 to 1955, famously disregarded the need for an ether altogether. Instead, he based his theory on two revolutionary postulates. The first postulate stated that the laws of physics are the same for all observers in uniform motion, meaning moving at a constant speed in a straight line. The second postulate, and the key to understanding the Michelson-Morley result, stated that the speed of a light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. Einstein's second postulate directly explained why Michelson and Morley found no ether wind. If the speed of light is a universal constant, fixed at approximately 299,792,458 meters per second, for all observers, then there is no need for a preferred medium or an absolute reference frame like the ether. The constant speed of light is a fundamental property of the universe itself, not dependent on any medium through which it travels. The Michelson-Morley experiment therefore did not merely fail to detect the ether, it provided crucial empirical evidence that supported the radical ideas that would later form the bedrock of modern physics. Its null result was not a failure of the experiment, but a triumph of scientific inquiry, as it forced a fundamental rethinking of space, time, and the nature of light. It paved the way for Einstein's theory of relativity, which fundamentally changed our understanding of the cosmos and established the speed of light not just as a very fast constant, but as an ultimate cosmic speed limit inherent to the fabric of space-time. The experiment stands as one of the most important experiments in physics, not for what it found, but for what it did not find, thereby opening the door to a new era of physics. In the mid-19th century, the fields of electricity, magnetism, and light were largely considered separate and distinct branches of physics. Experiments had revealed various phenomena related to electric charges, magnetic forces, and the propagation of light, but no unifying framework existed. It was the Scottish mathematician and physicist James Clerk Maxwell, who lived from 1831 to 1879, who brilliantly synthesized these disparate observations into a single, elegant, and revolutionary theory. His work, encapsulated in a set of 4 fundamental equations, not only unified electricity and magnetism, but also revealed the true nature of light as an electromagnetic wave and inherently predicted its constant speed in a vacuum. Before Maxwell, several key discoveries had laid the groundwork. In the early 19th century, Hans Christian Ørsted, a Danish physicist, discovered that electric currents produce magnetic fields. Shortly after, André-Marie Ampère, a French physicist and mathematician, developed mathematical laws describing the magnetic forces between electric currents. Michael Faraday, an English scientist, made seminal discoveries about electromagnetism, showing that changing magnetic fields could induce electric currents, a phenomenon known as electromagnetic induction. He also introduced the concept of lines of force, or fields, moving away from the idea of action at a distance to a more localized interaction in space. These discoveries established a strong link between electricity and magnetism, but a comprehensive theory was still lacking. Maxwell's genius lay in his ability to take these empirical laws, along with his own theoretical insights, and express them in a coherent mathematical framework. He recognized the profound interconnectedness of electric and magnetic phenomena through a series of papers culminating in his monumental treatise, A Treatise on Electricity and Magnetism, published in 1873. Maxwell presented his 4 equations. These equations are not just a collection of formulas, they are a concise summary of all classical electromagnetic phenomena. Let us describe the essence of each of Maxwell's 4 equations in simple terms. The first equation, often called Gauss's law for electricity, describes how electric charges create electric fields. It states that electric field lines originate from positive charges and terminate on negative charges. It essentially quantifies the concept that electric charges are the sources or sinks of electric fields. If you enclose a region of space, the total electric field passing through the boundary of that region is directly proportional to the total electric charge contained within that region. This equation explains why electric fields exist around charged objects. The second equation, Gauss's law for magnetism, is the magnetic counterpart. It states that there are no magnetic monopoles. In simpler terms, magnetic field lines always form continuous loops. They do not begin or end at a point. This means you can never find an isolated north pole or south pole of a magnet. Magnetic poles always come in pairs. If you enclose a region of space, the total magnetic field passing through its boundary will always be zero, because any magnetic field line entering the region must also exit it. The third equation is Faraday's law of induction. Building on Faraday's experimental work, this equation describes how a changing magnetic field creates an electric field. It is the principle behind electric generators and transformers. If a magnetic field in a region changes over time, it will generate an electric field that curls around the changing magnetic field. This is how moving a magnet near a coil of wire can produce an electric current. The fourth equation is Ampere's law with Maxwell's addition, often called the Ampere-Maxwell law. Ampere had previously shown that electric currents create magnetic fields that curl around the current. Maxwell's crucial insight here was to add a new term to Ampere's law. He proposed that a changing electric field also creates a magnetic field. This concept, known as the displacement current, was purely theoretical at the time, but it proved to be a stroke of genius. Without this term, Maxwell's theory would not have been complete, and it would not have predicted the existence of electromagnetic waves. A changing electric field, like a changing magnetic field, can induce the other, creating a self-sustaining cycle. The profound implication of Maxwell's four equations, particularly the last two, Faraday's law and the Ampere-Maxwell law, was that changing electric fields produce changing magnetic fields, and changing magnetic fields produce changing electric fields. This meant that once an electromagnetic disturbance was created, it could propagate through space, with the oscillating electric and magnetic fields continuously regenerating each other. This self-sustaining oscillation was in essence an electromagnetic wave. What was truly astonishing was that when Maxwell calculated the speed at which these theoretical electromagnetic waves should travel through a vacuum, he found a remarkable result. The speed was determined by two fundamental constants, derived from experiments related to electricity and magnetism: the permittivity of free space, which describes how an electric field passes through empty space, and the permeability of free space, which describes how a magnetic field passes through empty space. These constants were measurable values from purely electrical and magnetic experiments, with no direct connection to light at that point. When Maxwell put the numerical values of these constants into his equations, the calculated speed for these theoretical electromagnetic waves turned out to be approximately 300,000 kilometers per second, about 186,000 miles per second. This was an electrifying moment in physics, because this calculated speed was almost exactly equal to the independently measured speed of light. This stunning coincidence led Maxwell to a revolutionary conclusion. Light itself must be an electromagnetic wave. He wrote in 1865, "This velocity is so nearly that of light that it seems we have strong reason to conclude that light itself, including radiant heat and other radiations if any, is an electromagnetic disturbance in the form of waves propagated through the electromagnetic field according to electromagnetic laws." Maxwell's theory provided a comprehensive explanation for light. It explained why light travels at such a specific and constant speed in a vacuum. This speed is dictated by the fundamental properties of empty space itself, represented by the electromagnetic constants. It also explained the transverse nature of light waves, oscillations perpendicular to the direction of travel, because electric and magnetic fields oscillate perpendicular to each other and perpendicular to the direction of the wave's motion. Furthermore, it predicted the existence of an entire spectrum of electromagnetic waves, extending beyond visible light, including radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, all travelling at the same speed in a vacuum. Maxwell's work also provided a theoretical basis for why the speed of light would be constant for all observers if they were measuring it relative to the electromagnetic field, which was assumed to fill all space. This idea was initially compatible with the concept of the luminiferous ether. as the ether could be seen as the medium in which these electromagnetic fields existed and propagated. For a time, it was thought that the ether was the physical manifestation of Maxwell's electromagnetic field. This gave the ether theory a strong boost, as it was now seen not just as a medium for light, but as the very foundation for all electromagnetic phenomena. However, the constant speed of light predicted by Maxwell's equations, coupled with the assumption of a stationary ether, created a profound theoretical tension that would lead to further breakthroughs. If light speed was always c relative to the ether, then an observer moving through the ether should measure a different speed. This was the very puzzle that the Michelson-Morley experiment sought to solve. The importance of Maxwell's equations cannot be overstated. They are considered one of the greatest achievements in physics. They unified seemingly disparate phenomena into a single, elegant theory, predicting the existence of electromagnetic waves and revealing the true nature of light. This unification had immense practical consequences, leading directly to the development of radio, television, radar, and all forms of wireless communication. Beyond their practical applications, Maxwell's equations set the stage for the next revolution in physics. While they predicted that light speed would be constant, based on fundamental constants, they did not by themselves fully explain why that speed would be constant for all observers, regardless of their motion. This particular constancy, confirmed by the null result of the Michelson-Morley experiment, was the crucial piece of the puzzle that would be solved by Albert Einstein's special theory of relativity. Einstein took Maxwell's prediction of a constant speed of light as a fundamental postulate, leading to a complete rethinking of space, time, and motion, and ultimately discarding the need for the ether altogether. The speed of light in a vacuum, often denoted by the letter c, is one of the most fundamental and intriguing constants in the universe. Its precise value, approximately 299,792,458 meters per second, is not an arbitrary number but is deeply rooted in the very fabric of space and the fundamental laws of electromagnetism. The mathematical derivation of this constant speed from purely electrical and magnetic principles was one of the most remarkable achievements of James Clerk Maxwell in the mid-19th century. This derivation not only revealed the electromagnetic nature of light, but also hinted at its unchanging constancy, a feature that would later become a cornerstone of modern physics. Before Maxwell's work, the speed of light had been measured through astronomical observations by Roemer in the late 17th century, and later with increasing accuracy by terrestrial experiments conducted by Fizeau and Foucault in the 19th century. These measurements provided a numerical value for light speed, but they did not explain why light travelled at that particular speed, nor did they fully illuminate its inherent constancy. Light was simply observed to move at an extraordinarily high velocity. Maxwell's revolutionary contribution, building upon the experimental work of pioneers like Michael Faraday, was to unify electricity and magnetism into a single comprehensive theory. He formulated a set of 4 partial differential equations, now universally known as Maxwell's equations, that describe how electric and magnetic fields are generated and how they interact. These equations elegantly encapsulate all classical electromagnetic phenomena. The power of Maxwell's equations lies in their ability to describe how changes in one type of field can induce the other. Specifically, Faraday's law of induction states that a changing magnetic field creates an electric field. Maxwell's crucial addition to Ampere's law, leading to the Ampere-Maxwell law, posited that a changing electric field also creates a magnetic field. This reciprocal relationship was the key insight. Imagine an oscillating electric charge. It creates an oscillating electric field. According to Maxwell's insight, this changing electric field generates an oscillating magnetic field. This newly generated magnetic field, being itself an oscillating field, then generates an oscillating electric field and so on. This continuous self-sustaining interplay between changing electric and magnetic fields allows an electromagnetic disturbance to propagate outwards from its source as a wave. When Maxwell looked at the mathematical form of his combined equations in a vacuum, without any charges or currents present, he found that they naturally led to a wave equation. A wave equation is a mathematical description that dictates how a disturbance, like a ripple in a pond or a vibration in a string, propagates through space and time. The solutions to this wave equation represented propagating oscillations of electric and magnetic fields, in other words, electromagnetic waves. Crucially, the speed at which these theoretical electromagnetic waves should travel was inherent in the structure of the wave equation itself. The speed was determined by two fundamental physical constants that characterize the properties of empty space with respect to electric and magnetic fields. These constants are 1. The permittivity of free space, often denoted by the Greek letter epsilon naught, E0. This constant describes how well an electric field can pass through a vacuum, or how much electric field is generated by a given charge in a vacuum. It is a measure of the vacuum's ability to permit electric field lines. Its numerical value is approximately 8.854 times 10 to the power of minus 12 farads per meter. 2. The permeability of free space, often denoted by the Greek letter mu0, ME0. This constant describes how well a magnetic field can pass through a vacuum, or how much magnetic field is generated by a given current in a vacuum. It is a measure of the vacuum's ability to permit magnetic field lines. Its numerical value is approximately 1.257 times 10 to the power of minus 6 henries per meter. These two constants, E0 and M0, were already known from independent electrical and magnetic experiments conducted in laboratories. They quantify the fundamental electrical and magnetic properties of empty space. Maxwell's equations revealed that the speed of the electromagnetic waves, C, was mathematically related to these constants by the simple formula C just real 1. 0 is 0. When Maxwell substituted the known numerical values for E0 and M0 into this formula, he calculated a speed of approximately 300,000 kilometers per second, 186,000 miles per second. This calculated speed was astonishingly close to the experimentally measured speed of light that had been determined by Roemer, Fizeau, and Foucault. This numerical agreement was no mere coincidence. It led Maxwell to the profound conclusion that visible light was not just a wave, but specifically an electromagnetic wave. It meant that the light we see is nothing more than rapidly oscillating electric and magnetic fields propagating through space. The fact that the speed of light emerged directly from these fundamental constants of empty space had revolutionary implications. It suggested that light speed was not dependent on the properties of a source or the motion of an observer, but rather on the intrinsic properties of the vacuum itself. This was a radical idea for the time. In classical physics, the speed of a wave typically depends on the medium through which it travels, and the relative motion between the source or observer and that medium. For instance, the speed of sound depends on the temperature and density of the air, and if you are moving relative to the air, the sound waves will appear to have a different speed. However, Maxwell's equations did not specify any particular medium for electromagnetic waves beyond the vacuum itself. The constants E0 and M0 refer to the properties of empty space. This implied that light speed, c, was a fixed fundamental constant, appearing to be the same regardless of the state of motion of the source producing the light or the observer measuring it. This was because the speed was determined by properties inherent to the fabric of spacetime itself, rather than by a material medium that could be traversed or moved relative to. This prediction of light's constant speed, independent of the source's motion, was consistent with observations from astronomy. For example, binary stars which orbit each other would show distorted light patterns if the speed of light emitted from them depended on the star's orbital velocity. Yet, no such distortions were observed. This suggested that light always travelled at the same speed, irrespective of how fast its source was moving. While Maxwell's theory implied this constancy, the full implications of regardless of the observer were not immediately grasped. In the context of 19th century physics, the existence of a luminiferous ether was still widely believed. The ether was thought to be the medium for these electromagnetic waves, and it was assumed to be stationary, providing an absolute reference frame. In this view, the speed c derived by Maxwell was the speed of light relative to the stationary ether. An observer moving through this ether would, according to classical velocity addition rules, expect to measure a different speed for light. This expectation led directly to experiments like the Michelson-Morley experiment. which aimed to detect Earth's motion through this presumed stationary ether by looking for variations in the measured speed of light. The stunning null result of that experiment, showing no variation in light speed regardless of Earth's motion, presented a profound challenge to the ether theory and the classical understanding of how velocities add. The fact that Maxwell's equations inherently yield a constant speed for light, derived from fundamental constants of empty space, without any reference to a moving source or observer, was revolutionary. It suggested that c was not just a speed, but a fundamental property of the universe. This intrinsic constancy, rather than being an outcome of a specific medium and relative motion, suggested that it was a universal speed limit, fixed by the underlying structure of reality. Maxwell's work thus set the stage for Albert Einstein's special theory of relativity. Einstein took the constancy of the speed of light, as implied by Maxwell's equations and confirmed by experiments like Michelson-Morley, not as a derived result from an ether, but as a fundamental postulate of nature. He asserted that the speed of light in a vacuum is invariant for all inertial observers. This bold assertion, stemming directly from the implications of Maxwell's work, led to the revolutionary consequences of relativity, profoundly changing our understanding of space, time, mass, and energy. In the early years of the 20th century, the world of physics found itself grappling with a profound conceptual conflict. On one side stood Isaac Newton's well-established laws of motion, which had successfully described the mechanics of the universe for over 2 centuries. These laws, and the principle of Galilean relativity derived from them, held that velocities simply add or subtract. If you are on a train moving at 60 miles per hour, and you walk forward at 5 miles per hour, your speed relative to the ground is 65 miles per hour. This seemed perfectly intuitive, and was confirmed by everyday experience. On the other side was James Clerk Maxwell's revolutionary theory of electromagnetism, which had triumphantly unified electricity, magnetism, and light. A crucial implication of Maxwell's equations was that light is an electromagnetic wave, and its speed in a vacuum, often denoted c, is a fixed constant, derived from the fundamental electrical and magnetic properties of empty space. This speed was calculated to be approximately 300,000 kilometers per second. The puzzle arose when trying to reconcile these two pillars of physics. If light speed was truly a constant c, as predicted by Maxwell's equations, what did this mean for observers moving at different speeds? According to Newton's classical mechanics and Galilean relativity, if a light source emitted light at speed c, and an observer was moving towards that source at a speed v, then the observer should measure the light approaching them at a speed of c plus v. Conversely, if the observer was moving away, they should measure cv. This simple velocity addition rule seemed logical, and was consistent with all other known forms of motion. However, Maxwell's equations themselves did not contain any variable for the observer's speed. They always predicted light to travel at c in a vacuum, regardless of the motion of the source. This inherent constancy in Maxwell's theory posed a direct challenge to the classical understanding of relative motion. This conflict was further exacerbated by the results of the Michelson-Morley experiment, performed in 1887. This experiment was designed to detect Earth's motion through a hypothetical luminiferous ether, which was thought to be the stationary medium through which light waves propagated. If the ether existed and provided an absolute reference frame, then light speed should vary depending on Earth's velocity relative to this ether. Yet, the experiment famously yielded a null result. No variation in the speed of light was detected, regardless of Earth's motion or the direction of measurement. The speed of light appeared to be the same for all observers, even those in different states of motion. This was the central puzzle that captivated Albert Einstein, a young patent clerk in Bern, Switzerland in 1905. Einstein, who lived from 1879 to 1955, was deeply troubled by this inconsistency. He recognized that there was a fundamental clash between the principle of Galilean relativity, which worked perfectly for mechanical phenomena, and the constant speed of light derived from Maxwell's electromagnetic theory, which was experimentally verified by Michelson-Morley. If both were true, it created a paradox. Many physicists at the time tried to resolve this conflict by modifying the properties of the ether, or by proposing ad hoc explanations like the Lorentz-Fitzgerald contraction, which suggested that objects physically contracted when moving through the ether. While these ideas could mathematically explain the Michelson-Morley result, they lacked a deeper unifying principle and seemed like patches to a crumbling theory. Einstein's genius lay in his willingness to question the most deeply held assumptions. Instead of trying to find a way to make the speed of light behave differently for moving observers, or to invent new properties for the ether, he proposed a radical solution. What if both Newton's principle of relativity and Maxwell's constant speed of light were fundamentally true, and that it was our everyday intuition about space and time that needed to be re-evaluated? Einstein's approach was to elevate two seemingly contradictory ideas into fundamental postulates, or starting points, for a new theory. The first postulate, known as the principle of relativity, stated that the laws of physics are the same for all observers in uniform motion, that is, moving at a constant velocity in a straight line. This was essentially an extension of Galileo's principle of relativity to all laws of physics, including those of electromagnetism. It meant that there is no preferred or absolute frame of reference, and no way to determine absolute motion. All uniform motion is relative. The second postulate, known as the principle of the constancy of the speed of light, stated that the speed of light in a vacuum, c, is the same for all inertial observers, regardless of the motion of the light source or the observer. This postulate directly incorporated the observation from Maxwell's equations and the Michelson-Morley experiment. By accepting these two postulates as inviolable truths, Einstein immediately resolved the conflict. If the speed of light is indeed a constant c for everyone, no matter their relative motion, then the classical rules for adding velocities must be wrong when dealing with speeds approaching c. This seemingly simple step had profound and counterintuitive consequences for our understanding of space and time. To maintain the constancy of the speed of light for all observers, Einstein showed that space and time themselves could not be absolute, as Newton had believed. Instead, they had to be relative and interconnected. This meant that 1. Time dilation. Time would pass differently for observers moving relative to each other. An observer in motion relative to another would experience time passing more slowly. For example, a clock on a spaceship moving at very high speed would tick slower compared to a clock on Earth, when observed from Earth. 2. Length contraction. The length of an object would appear to shrink in the direction of its motion when observed by someone moving relative to it. A spaceship moving at very high speed would appear shorter to an observer on Earth in the direction of its travel. 3. Relativistic mass increase. The mass of an object would appear to increase as its speed approached the speed of light. As an object gained speed, it would become more massive, requiring increasingly more force to accelerate it further. This implied that an infinite amount of energy would be required to accelerate any object with mass to the speed of light, making it an unreachable barrier. These consequences, derived directly from the two postulates, were not merely mathematical quirks. They described a deeper reality where space and time are intertwined into a single entity called space-time. The speed of light, c, emerges not just as the speed of light particles, but as the fundamental speed limit of the universe, representing the maximum speed at which any information or energy can travel. It is the conversion factor between space and time dimensions. Einstein's theory completely discarded the concept of the ether. If the speed of light is constant for all observers, there is no need for a fixed medium through which it travels. Light propagates through the vacuum of space, governed by the intrinsic properties of space-time, not by a physical substance. The ether, a concept that had plagued physics with its contradictory properties, became obsolete. The solution to Einstein's puzzle was therefore not to modify light's behaviour or invent new properties for the ether, but to fundamentally revise our understanding of space and time. Newton's laws of motion were not wrong, but they were approximations that worked very well at everyday speeds. At speeds approaching the speed of light, Einstein's relativistic laws take over, revealing a universe where space and time are flexible and intertwined, all conspiring to ensure that the speed of light remains constant for all observers. Einstein's special theory of relativity provided a consistent and elegant framework that resolved the conflict between Maxwell's electromagnetism and Newton's mechanics. It explained the null result of the Michelson-Morley experiment as a direct consequence of the universe's fundamental structure, rather than an experimental anomaly. This revolutionary theory laid the foundation for much of modern physics, from particle accelerators to GPS technology, and reshaped humanity's understanding of the universe. The constancy of C was no longer just a curious measured value, it became a defining characteristic of space-time itself, leading directly to the realization that nothing can travel faster than light. In the early years of the 20th century, the scientific understanding of the universe faced a significant challenge. Two pillars of physics, which had served so well for centuries, seemed to be in conflict. On one side, there were Isaac Newton's laws of motion, formulated in the late 17th century, which described how objects move and interact under forces. These laws were incredibly successful in explaining everything from the fall of an apple to the orbits of planets. Embedded within Newtonian mechanics was the principle of Galilean relativity, which stated that the laws of physics are the same for all observers moving at a constant speed in a straight line. This meant that if you were inside a windowless train moving smoothly, you couldn't tell if you were moving or standing still by performing experiments inside the train. Furthermore, it implied that velocities simply added or subtracted. If a person walked at 5 miles per hour towards the front of a train moving at 60 miles per hour, their speed relative to the ground would be 65 miles per hour. This concept of relative motion seemed perfectly intuitive and aligned with everyday experience. On the other side was James Clerk Maxwell's theory of electromagnetism, developed in the mid-19th century. Maxwell's equations unified electricity and magnetism and, most remarkably, predicted that light itself was an electromagnetic wave. Crucially, these equations also showed that the speed of this electromagnetic wave in a vacuum, often denoted by the letter c, was a constant value, approximately 300,000 kilometers per second. This speed was derived directly from fundamental constants related to the electrical and magnetic properties of empty space. The puzzle was that Maxwell's equations predicted this speed is c, regardless of the motion of the source emitting the light. This was different from other waves. For example, the speed of sound depends on the medium it travels through, and if the source of the sound is moving, the perceived speed of the sound waves can change for a stationary observer, the Doppler effect. The conflict became even more pronounced with the results of the Michelson-Morley experiment performed in 1887. This experiment was designed to detect the hypothetical luminiferous ether, an invisible medium that was thought to fill all space and through which light waves supposedly travelled. If this ether existed and was stationary, then Earth's motion through it should cause a detectable ether wind, leading to variations in the measured speed of light depending on the direction of measurement. However, the Michelson-Morley experiment yielded a null result. No such variations were detected. The speed of light appeared to be the same in all directions regardless of Earth's motion. This experimental finding profoundly challenged the ether theory and indicated a deep inconsistency between classical mechanics and electromagnetism. It was into this scientific climate that Albert Einstein, then a young patent clerk in Bern, Switzerland, stepped forward in 1905 with his special theory of relativity. Einstein, a brilliant thinker who lived from 1879 to 1955, recognized the inherent contradiction. Instead of trying to invent complicated explanations for the ether, or to force Maxwell's electromagnetism to fit within Newtonian physics, Einstein proposed a radical solution. He chose to accept the empirical evidence and the implications of Maxwell's theory as fundamental truths about the universe. He discarded the need for an ether altogether. Einstein's special theory of relativity is built upon two core ideas, or postulates. The first postulate, the principle of relativity. This postulate states that the laws of physics are the same for all observers in uniform motion. An observer in uniform motion refers to someone moving at a constant velocity in a straight line, without accelerating. Such a frame of reference is called an inertial frame. This postulate is an extension of Galileo's earlier principle of relativity, but Einstein extended it to cover all laws of physics, including those of electromagnetism. What this means is that there is no absolute rest or motion in the universe. If you're in a windowless spaceship drifting through space at a constant speed, there is no experiment you can perform inside your spaceship that will tell you whether you are moving or standing still. The laws of motion, electromagnetism, and all other physical laws will operate exactly the same way within your spaceship as they would in a spaceship that is truly at rest, if such a thing existed. This postulate implies that there is no privileged or absolute reference frame in the universe. All inertial frames are equally valid. The second postulate, the principle of the constancy of the speed of light. This postulate states that the speed of light in a vacuum, c, is the same for all inertial observers, regardless of the motion of the light source or the observer. This is the truly revolutionary idea. It means that if a light bulb emits light, and you are standing still, you will measure the light speed as c. If you are moving towards the light bulb at a very high speed, you will still measure the light speed as c. And if you are moving away from the light bulb, you will still measure the light speed as c. This directly contradicts our everyday intuition and the classical rules of velocity addition. It's like saying if a car is driving towards you at 60 miles per hour and you run towards it at 10 miles per hour, you would still perceive the car approaching you at exactly 60 miles per hour, which is completely counter to our experience with normal objects. But light is not a normal object in this sense. The Michelson-Morley experiment had already provided strong evidence for this constancy, even if its implications were not fully understood at the time. By accepting these two postulates as fundamental truths, Einstein was able to derive a series of profound and often counterintuitive consequences that fundamentally changed our understanding of space, time, mass, and energy. These consequences are not assumptions. They are logical deductions that must follow if the two postulates are correct. One of the most striking consequences is the relativity of simultaneity. In classical physics, if two events happen at the exact same moment for one observer, they happen at the exact same moment for all observers, regardless of their motion. Time was considered absolute and universal. However, in special relativity, if two events are simultaneous for one observer, they may not be simultaneous for another observer who is moving relative to the first. For example, imagine a long train moving at high speed and a light flash occurs exactly in the middle of the train. For an observer inside the train, equidistant from both ends, the light will reach the front and back of the train at the same moment. They will perceive these two events, light reaching front, light reaching back, as simultaneous. But for an observer standing on the ground as the train passes by, the light travelling to the front of the moving train has to cover a greater distance, and the light travelling to the back of the train has to cover a shorter distance. Since the speed of light is constant for the ground observer as well, the light will reach the back of the train before it reaches the front. Thus, the two events that were simultaneous for the train observer are not simultaneous for the ground observer. Simultaneity is relative. It depends on the observer's frame of reference. Another profound consequence is time dilation. This concept directly challenges the idea of absolute time. Special relativity predicts that time passes more slowly for an object that is moving very fast, relative to an observer who is not moving with it. If you were able to travel in a spaceship at a speed very close to the speed of light and then return to Earth, you would find that less time had passed for you than for those who remained on Earth. Your clocks would have run slower, and you would have aged less. We will delve much deeper into time dilation in the next chapter, but it is a direct and unavoidable consequence of the constancy of the speed of light. To ensure that light always travels at c for all observers, time itself must stretch or contract depending on relative motion. Similarly, length contraction is another consequence. Special relativity predicts that the length of an object, when measured by an observer moving relative to it, will appear to be shorter in the direction of its motion. If that same spaceship were flying past Earth at very high speed, observers on Earth would measure its length to be shorter than its length when it is at rest. This contraction only occurs in the direction of motion. The dimensions perpendicular to motion are unaffected. Again, this effect is only noticeable at speeds very close to the speed of light. Perhaps the most famous outcome of special relativity is the mass-energy equivalence expressed by the iconic equation E mc2. This equation states that energy, E, and mass, m, are interchangeable. They are two forms of the same thing. The C2 term, the speed of light squared, is a conversion factor, indicating that a small amount of mass can be converted into an enormous amount of energy, and vice versa. This equation explained the immense energy released in nuclear reactions, like those in atomic bombs and stars. It showed that as an object approaches the speed of light, its effective mass increases, making it increasingly difficult to accelerate further. This relativistic mass increase implies that it would take an infinite amount of energy to accelerate any object with mass to the speed of light, hence reinforcing C as an ultimate speed limit for anything with mass. Special relativity also introduces a different way to combine velocities, known as relativistic velocity addition. The simple classical rule of adding velocities, like the person walking on a train, breaks down at high speeds. In special relativity, if you're in a spaceship moving at half the speed of light, 0.5 c, and you fire a projectile from your ship at half the speed of light relative to your ship, 0.5 c, the projectile's speed relative to a stationary observer would not be 1.0 c, the speed of light. Instead, it would be about 0.8 c. The formula for relativistic velocity addition ensures that the combined speed never exceeds c, no matter how close to c the individual velocities are. This mathematical framework ensures consistency with the second postulate, upholding the constant speed of light. A crucial implication of special relativity is the complete abolition of the concept of an absolute space and absolute time. Newton believed in a universal fixed reference frame against which all motion could be measured, and a universal clock that ticked uniformly for everyone. Einstein showed that these absolute concepts are illusions. Space and time are not independent entities. Instead, they are interwoven into a four-dimensional fabric called spacetime. Events occur at specific points in spacetime, defined by three spatial coordinates and one time coordinate. The separation between events, known as the spacetime interval, is what remains invariant for all observers. Different observers may disagree on the individual spatial distances or time durations between two events, but they will always agree on the spacetime interval between them. This means that space and time are relative, but spacetime itself is an invariant fundamental structure. The abandonment of the ether, which the Michelson-Morley experiment indirectly showed to be non-existent, was a direct consequence of these postulates. If the speed of light is constant for all observers, then there is no need for a special medium to carry light waves, nor is there a preferred frame of reference. Light is simply a disturbance in the electromagnetic field that propagates through the vacuum of space at a fixed speed, a speed that is an inherent property of the universe's fabric rather than dependent on a medium. Special relativity is called special because it only applies to inertial frames of reference, that is, observers moving at constant velocity in a straight line. It does not account for acceleration or gravity. Einstein later developed his general theory of relativity to incorporate gravity and accelerating frames, building upon the principles of special relativity. Despite its initial counterintuitive nature, special relativity has been rigorously tested and confirmed by countless experiments and observations over the past century. Its predictions are not just theoretical curiosities, but are crucial for the functioning of modern technology, such as the Global Positioning System, or GPS. GPS satellites orbit Earth at speeds high enough for relativistic effects to be noticeable. Without accounting for time dilation, both special and general relativistic effects, GPS devices would quickly become inaccurate, accumulating errors of many meters per day. The impact of special relativity on physics and human understanding has been profound. It revolutionized our concepts of space, time, mass, and energy, demonstrating their interconnectedness and relativity. It revealed that the universe operates on principles that defy everyday intuition, but are mathematically consistent and experimentally verifiable. The speed of light, c, went from being a mere numerical value to being a fundamental constant that defines the very structure of spacetime and acts as the ultimate speed limit for anything with mass, shaping the possibilities of motion and communication across the cosmos. It stands as a testament to the power of abstract thought, based on simple postulates, to uncover the deepest truths about reality. One of the most mind-bending and revolutionary consequences of Albert Einstein's special theory of relativity is the phenomenon known as time dilation. This concept fundamentally challenges our intuitive understanding of time as a universal absolute quantity that ticks away at the same rate for everyone, everywhere. Instead, special relativity reveals that time is relative. its passage depends on the relative motion between observers. Specifically, time dilation means that for an observer in motion relative to another, time will appear to pass more slowly for the moving observer. This effect is not a trick of perception or an optical illusion. It is a genuine stretching of time itself, a direct consequence of the two fundamental postulates of special relativity. To fully grasp time dilation, it is important to recall those two postulates. The first is the principle of relativity, which states that the laws of physics are the same for all observers moving at a constant speed in a straight line, inertial frames. The second, and perhaps more crucial for time dilation, is the principle of the constancy of the speed of light, which asserts that the speed of light in a vacuum, c, is the same for all inertial observers, regardless of the motion of the light source or the observer. It is this unwavering constancy of light speed that forces time to behave in such a peculiar way. To illustrate time dilation without complex mathematics, we can use a simple and famous thought experiment involving a light clock. Imagine a clock that works by a pulse of light bouncing between two parallel mirrors. Let's say the mirrors are 1 meter apart. A light pulse starts from the bottom mirror, travels to the top mirror, reflects off it, and returns to the bottom mirror. Each round trip of the light pulse represents 1 tick of the clock. Since the distance between the mirrors is fixed, and the speed of light c is constant, the time it takes for 1 tick, the round trip, is simply twice the distance divided by the speed of light. Now consider two observers. One observer, whom we can call Alice, is stationary relative to the light clock. She holds the clock, and for her, the light pulse simply moves vertically up and down between the mirrors. She measures the time for 1 tick as we just described, a value we can call her proper time. Now imagine a second observer, whom we can call Bob, who is moving at a very high, constant speed horizontally past Alice, carrying an identical light clock. From Bob's perspective, his light clock is stationary, and its light pulse also simply moves vertically up and down, just as Alice sees her clock. Bob also measures the time for 1 tick on his clock as his proper time. However, things look different from Alice's perspective when she observes Bob's moving light clock. Because Bob's clock is moving horizontally, the light pulse in his clock does not just travel straight up and down. From Alice's point of view, the light pulse must travel a diagonal path to go from the bottom mirror to the top mirror and back again. While the mirrors are moving horizontally, the light still has to travel the vertical distance between them, but it also has to cover the horizontal distance that the mirrors move during the time the light is in transit. This results in a longer path length for the light pulse in Bob's moving clock, as seen by Alice. Here is the crucial point. According to the second postulate of special relativity, the speed of light is the same for both Alice and Bob. Both observers must measure the light pulse travelling at c. Alice sees the light pulse in Bob's clock travel a longer diagonal path. If the light travels a longer distance and its speed is still c, the same speed as the light in her own stationary clock, then it must take a longer amount of time to complete 1 tick. Therefore, from Alice's perspective, Bob's moving light clock ticks more slowly than her own stationary light clock. Time itself has dilated for Bob's moving clock as observed by Alice. This is the essence of time dilation. Time slows down for a moving object, as observed from a stationary frame. The faster an object moves, the more dramatically time slows down for it. This effect only becomes significant at speeds approaching the speed of light. At everyday speeds, the effect is so tiny that it is imperceptible. For example, if a car drives past you at 100 km per hour, its clock runs only a minuscule fraction of a second slower than yours over millions of years. The factor by which time dilates is given by the Lorentz factor, represented by the Greek letter gamma, dr. This factor depends on the speed of the moving object relative to the speed of light. As the object's speed approaches c, the Lorentz factor increases dramatically, causing time to slow down more and more. If an object could reach the speed of light, the Lorentz factor would become infinite, implying that time would stop completely for that object, as seen by a stationary observer. A common point of confusion arises from the apparent symmetry of the situation. If Alice sees Bob's clock running slow, doesn't Bob also see Alice's clock running slow? Yes, he does. From Bob's perspective, he is stationary, and Alice is moving past him at a high speed. By the same logic of the light clock thought experiment, Bob observes that Alice's clock is ticking more slowly than his own. This is known as the reciprocity of time dilation. Each observer genuinely measures the other's clock to be running slower. This symmetry is perfectly consistent with the first postulate, which states that the laws of physics are the same for all inertial observers. There is no preferred frame, each considers themselves stationary and the other moving. This leads to the famous twin paradox. Imagine identical twins, Alice and Bob. Alice stays on Earth, while Bob takes a spaceship on a long, high-speed journey to a distant star and back. According to time dilation, Alice would observe Bob's clock running slow, meaning Bob would age less during his trip. But from Bob's perspective, he was stationary, and it was Alice and Earth who moved away and then came back. So, shouldn't Bob observe Alice aging less? The paradox seems to arise because of the apparent symmetry. The resolution to the twin paradox lies in recognizing that the situation is not perfectly symmetrical. While Alice remains in a single inertial frame throughout the entire experiment, Bob does not. Bob's journey involves acceleration. He must accelerate to leave Earth, decelerate to turn around at the distant star, and then accelerate again to return to Earth, finally decelerating upon arrival. It is this acceleration that breaks the symmetry. An observer who undergoes acceleration or changes inertial frames is in a fundamentally different situation than an observer who remains in a single inertial frame. It is the accelerating twin, Bob, who experiences the actual time difference and ages less. The paradox is resolved within the framework of special relativity by carefully accounting for the non-inertial parts of the journey. The accelerations mean that Bob's frame of reference changes, and he is able to feel those accelerations, distinguishing his experience from Alice's. Time dilation is not just a theoretical concept or a mathematical curiosity. It has been rigorously confirmed by numerous experiments and observations. One of the most compelling pieces of evidence comes from the study of subatomic particles called muons. Muons are unstable particles similar to electrons but much more massive. They are created naturally in Earth's upper atmosphere when cosmic rays collide with air molecules. Muons have a very short half-life, meaning they decay into other particles very quickly. In their own reference frame, their proper time, they exist for only about 2.2 microseconds, 2.2 millionths of a second. Based on this incredibly short lifetime and their typical speed of about 99% the speed of light, classical physics would predict that muons created in the upper atmosphere should travel only a few hundred meters before decaying. Therefore, very few, if any, should reach Earth's surface. However, experiments show that a significant number of muons do reach Earth's surface. This is direct evidence of time dilation. From the perspective of an observer on Earth, the muons are travelling at extremely high speeds. Therefore, time for the muons is dilated, slowed down, relative to Earth's frame. This means that from Earth's perspective, the muons' lifetimes are extended, allowing them to travel much greater distances, many kilometers, before decaying. Without time dilation, the observed flux of muons at the surface would be far lower than what is actually measured. Particle accelerators also confirm this. Muons created in laboratories and accelerated to near light speed are observed to have extended lifetimes, precisely in accordance with the predictions of special relativity. Another strong piece of evidence for time dilation comes from experiments with highly precise atomic clocks. In 1971, Joseph Haefel and Richard Keating conducted a famous experiment. They synchronized 4 atomic clocks and then flew 2 of them on commercial airliners, one eastward around the world and one westward. 2 clocks remained stationary on the ground. When the travelling clocks returned, they were compared to the stationary clocks. The results showed that the flying clocks had indeed measured slightly different amounts of time compared to the ground-based clocks, precisely as predicted by special relativity, and also general relativity, which accounts for gravitational effects on time. The clocks that flew eastward, moving with Earth's rotation, thus having a higher effective speed relative to the Earth's centre, lost a tiny amount of time, while those that flew westward, moving against Earth's rotation, thus having a lower effective speed relative to the Earth's centre, gained a tiny amount of time. These minuscule differences, measured in nanoseconds, billionths of a second, were exactly as predicted by Einstein's theories. Perhaps the most pervasive practical application of time dilation, which affects billions of people daily, is the Global Positioning System, or GPS. GPS satellites orbit Earth at speeds of about 14,000 kilometers per hour, about 8,700 miles per hour. While this speed is far less than the speed of light, it is still fast enough for special relativistic effects to be significant. The atomic clocks on board GPS satellites, if uncorrected, would run slower than identical clocks on Earth by about 7 microseconds, 7 millionths of a second, per day due to time dilation. While this might seem small, it would lead to errors in position calculations accumulating to many meters per day, rendering GPS useless for precise navigation within minutes. To ensure GPS accuracy, the software in the satellites and receivers constantly compensates for these relativistic time dilation effects, along with effects from general relativity due to gravity. Why do we not experience time dilation in our everyday lives? The reason is that our everyday speeds are incredibly slow compared to the speed of light. For time dilation to be noticeable, an object must be moving at a significant fraction of the speed of light, typically 10% or more. Even the fastest jets or rockets achieve speeds that are a tiny fraction of c. At such low speeds, the Lorentz factor is extremely close to 1, meaning the time dilation effect is infinitesimally small and impossible to detect without incredibly precise scientific instruments. Our classical intuition about absolute time works perfectly fine for the speeds we encounter in daily life. The implications of time dilation are profound. It means that time is not a universal fixed rhythm, but a flexible dimension that can be stretched or compressed depending on relative motion. This concept reshapes our understanding of aging, travel, and even the lifespan of subatomic particles. It means that future interstellar travelers, if they could achieve speeds close to light, would experience significantly less time passing during their journeys than those who remained on their home planet. While they would not feel time slowing down for themselves, their own clocks and biological processes would still feel normal to them. Upon returning, they would find that many more years had passed on their homeworld. Time dilation is a cornerstone of special relativity, a bizarre yet undeniably real phenomenon that highlights the universe's truly remarkable and counterintuitive nature when observed at extreme speeds. Length contraction is another fascinating and highly counterintuitive consequence of Albert Einstein's special theory of relativity. Just as time dilation reveals that time itself is not absolute but relative to an observer's motion, length contraction shows that space, or more precisely the dimensions of objects in space, are also relative. Specifically, special relativity predicts that an object moving at very high speeds will appear shorter in the direction of its motion to an observer who is not moving with it. This effect is genuine and measurable, not merely an optical illusion. It arises directly from the two fundamental postulates of special relativity: the principle that the laws of physics are the same for all observers in uniform motion, and the principle that the speed of a light in a vacuum is constant for all inertial observers. To understand length contraction, it is helpful to reconsider the same thought experiment involving a moving object and observers in different frames of reference, always keeping in mind the unyielding constancy of the speed of light. Imagine a spaceship travelling at a very high, constant speed through space. Inside the spaceship, an astronaut is measuring the length of the ship using a ruler. For this astronaut, who is at rest relative to the spaceship, the length measured is what is called the proper length, or rest length. This is the length of an object measured in its own rest frame. Now consider an observer on a stationary space station, watching the spaceship fly by. For this stationary observer, the spaceship is moving at a very high speed. If the observer on the space station tries to measure the length of the spaceship as it zooms past, they will find that the spaceship appears shorter than its proper length. This shortening occurs only in the direction of the spaceship's motion. Its height and width, perpendicular to the direction of travel, remain unchanged. The faster the spaceship moves, the more pronounced this shortening effect becomes. This phenomenon is a direct consequence of the constancy of the speed of light and the relativity of simultaneity. To illustrate, let us imagine another thought experiment involving measuring length. Consider a long train moving at a very high speed. An observer standing on the ground wants to measure the length of this moving train. To do this, the ground observer would need to mark the positions of the front and back of the train at the same instant according to their own clock. If they mark the front and back at different times, the train would have moved, and the measurement would be inaccurate. However, as we learned in the discussion of the relativity of simultaneity, two events that are simultaneous for one observer are not necessarily simultaneous for an observer in relative motion. For the ground observer, marking the front and back of the moving train simultaneously is critical to measuring its length. But for an observer on the train, those two markings on the ground, made simultaneously by the ground observer, would not appear simultaneous. This difference in perception of simultaneity is what leads to the measured length contraction. From the perspective of the ground observer, if the train were not contracted, then for the constant speed of light to hold, for both the observer on the train and the observer on the ground, some peculiar things would have to happen with time. If the train's length remained the same, then for light to cover its length in a consistent way for both observers, time would have to behave differently. Length contraction is the universe's way of ensuring that the speed of light remains constant for all observers, regardless of their relative motion. Let's use a light-based thought experiment for length, similar to the light clock. Imagine an astronaut on a moving spaceship trying to measure the length of their ship. They could do this by sending a light signal from the front of the ship to a mirror at the back, and timing how long it takes for the light to return. In the astronaut's frame of reference, where the ship is at rest, the light travels to the back and reflects back in a certain amount of time, giving a proper length. Now, let's consider this same event from the perspective of a stationary observer outside the ship. For this observer, the ship is moving. When the light is sent from the front of the ship towards the back of the ship is moving away from the light source. This means the light has to chase the back of the ship for a short distance before it hits the mirror. Then, on the return trip, the front of the ship, where the sensor is moving towards the incoming light, so the light has a shorter distance to cover before it is detected. Because the speed of light must be constant for the stationary observer as well, and because the light has to cover different effective distances in its outbound and inbound journeys due to the ship's motion, the total time for the light to make the round trip, as measured by the stationary observer, will be different from the time measured by the astronaut on the ship. The only way for the stationary observer to reconcile this and still maintain the constant speed of light, c, is if the length of the spaceship itself appears to be shorter in the direction of its motion. The formula for length contraction involves the same Lorentz factor, gamma, g, that governs time dilation. The observed length, L, is equal to the proper length, L0, the length at rest, divided by the Lorentz factor, L cern L0, g. Since the Lorentz factor is always greater than or equal to 1 for any relative motion, the observed length L will always be less than or equal to the proper length L0. The faster the object moves, the larger the Lorentz factor becomes, and the more severe the contraction. If an object were to reach the speed of light, its length in the direction of the motion would contract to 0, which is another reason why objects with mass cannot reach c. It is important to emphasize that length contraction is not just an optical illusion caused by light taking time to reach the observer. It is a genuine relativistic effect on the fabric of space-time. If you could somehow instantaneously stop the moving object and measure its length, you would find it to be its proper length. But as long as it is in motion relative to your frame, its length along its direction of travel is genuinely contracted from your perspective. Like time dilation, length contraction is only noticeable at speeds that are a significant fraction of the speed of light. For objects moving at everyday speeds, even very fast ones like airplanes or satellites, the effect is infinitesimally small and completely imperceptible. For example, a commercial airliner flying at about 900 km per hour would experience a length contraction of only a few atomic diameters, which is immeasurable with current technology. However, for particles moving at 99.9% the speed of light, the contraction is very significant, and the object's length could appear to be reduced to just a few percent of its original length. One of the best examples of length contraction in action comes from the same phenomenon that demonstrates time dilation, the behavior of muons. Muons are unstable subatomic particles created in Earth's upper atmosphere by cosmic rays. They travel towards Earth's surface at speeds very close to the speed of light. From the perspective of an observer on Earth, muons exhibit time dilation, meaning their internal clocks, and thus their lifetimes, run slower, allowing them to travel much further than their short, proper lifetime would classically allow. Now, let's consider the same phenomenon from the perspective of the muon itself. In the muon's own frame of reference, its lifetime is normal and short, about 2.2 microseconds. However, from the muon's perspective, it is Earth's atmosphere that is rushing towards it at nearly the speed of light. To the muon, the atmosphere, and thus the distance it needs to travel to reach the surface, is length contracted. So, from the muon's point of view, the distance from where it is created in the upper atmosphere to the Earth's surface is much shorter than what a stationary observer on Earth would measure. This length contraction of the atmosphere, the distance, allows the muon to reach the surface within its very short proper lifetime. Both time dilation, from Earth's perspective, and length contraction, from the muon's perspective, provide consistent explanations for why muons reach the ground, demonstrating the deep interconnectedness of space and time in special relativity. Length contraction is also relevant in particle accelerators. When particles are accelerated to speeds extremely close to the speed of light, the experimental equipment itself, from the perspective of the moving particles, appears to be length contracted. For instance, the particles might perceive the miles-long circular tunnels of accelerators like the Large Hadron Collider as being much shorter due to their extreme speed. This has to be taken into account in the design and operation of such machines. The concept of length contraction challenges our deeply ingrained intuitive understanding of space as absolute and unchanging. It shows that the dimensions of objects are not fixed but are relative to the observer's state of motion. An object has its proper length when measured in its own rest frame, but its length will appear contracted to any observer moving relative to it. This effect is reciprocal. Just as Alice sees Bob's spaceship contracted, Bob sees Alice's space station contracted in its direction of motion relative to him. These effects are not arbitrary. They are the natural consequence of the constancy of the speed of light, ensuring that the fundamental laws of physics hold true for all inertial observers. Length contraction, along with time dilation, illustrates how special relativity revolutionized our perception of reality, revealing space and time as flexible, interconnected aspects of a larger entity called space-time. Another profound and often surprising consequence of Albert Einstein's special theory of relativity is the prediction that an object's mass increases as its speed approaches the speed of light. This phenomenon, known as relativistic mass increase, has crucial implications. It explains why no object with mass can ever reach or exceed the speed of light, establishing c as the ultimate speed limit in the universe. This effect, like time dilation and length contraction, is a direct outcome of Einstein's two postulates: the constancy of the speed of light and the principle that the laws of physics are the same for all observers in uniform motion. In classical Newtonian physics, the mass of an object is considered a fixed and intrinsic property, independent of its motion. Whether an object is at rest or moving, its mass is assumed to be constant. Newton's second law of motion states that force equals mass times acceleration, FMA, implying that a constant force applied to a constant mass would produce a constant acceleration. However, as physicists began to explore the implications of light's constant speed and the Michelson-Morley experiment's null result, it became clear that classical mechanics needed to be revised for objects moving at very high speeds. Einstein's special relativity reveals that the concepts of mass, energy, momentum, and speed are deeply intertwined. As an object accelerates and gains speed, its kinetic energy increases. In classical physics, this kinetic energy is purely related to its motion. In special relativity, however, energy and mass are interconvertible, famously described by the equation EImc². This equation implies that mass itself is a form of energy, and energy can manifest as mass. Consider an object being pushed by a constant force. According to Newton, it would continue to accelerate uniformly. But what happens as its speed gets closer and closer to the speed of light, sc? If it continued to accelerate uniformly, it would eventually surpass c. However, the second postulate of special relativity dictates that nothing can travel faster than the speed of light in a vacuum. To reconcile this, something fundamental about the object must change. That something is its effective mass. As an object's speed increases, its relativistic mass, m, increases relative to its rest mass, m0, its mass when it is stationary. The formula for relativistic mass is m plus m0, 1 v2 to c2, where v is the object's speed and c is the speed of light. The term in the denominator, 1 rho to c2, is the inverse of the Lorentz factor, grus, so the formula can also be written as m down grem das 0. Let's examine what this formula implies. 1. At low speeds. When an object's speed v is very small compared to the speed of light c, the term v2c2 is extremely small, almost 0. In this case, 1 v2 c2 is very close to 1. Therefore the relativistic mass m is almost equal to the rest mass m zo. This is why we do not observe mass increase in our everyday lives. Classical Newtonian physics works perfectly well at low speeds. 2. As speed increases. As v increases and gets closer to c, the term v2c2 becomes a significant fraction, and 1 v2c2 becomes smaller. Since this term is in the denominator, dividing by a smaller number makes the relativistic mass m larger. 3. At the speed of light. If an object with rest mass were to reach the speed of light, v would equal c. Then v2c2 would be 1, and the denominator 1 would be 0. Dividing by 0 results in an infinite mass. This means that accelerating an object with rest mass to the speed of light would require an infinite amount of energy, which is impossible. Therefore, it is physically impossible for any object that has a non-zero rest mass to ever reach or exceed the speed of light. This relativistic mass increase is not about an object getting physically heavier in the sense of more atoms being added to it. Rather, it represents an increase in its inertia, its resistance to further acceleration. As an object moves faster, more and more of the energy put into accelerating it goes into increasing its mass rather than increasing its speed. It becomes progressively harder to accelerate the object further. The concept of relativistic mass increase is most clearly observed and verified in particle accelerators, such as the Large Hadron Collider or Fermilab. These machines accelerate subatomic particles like electrons and protons to speeds extremely close to the speed of light. For example, electrons in these accelerators can reach speeds of 99.999999% of the speed of light. At such speeds, their relativistic mass can be thousands or even hundreds of thousands of times greater than their rest mass. Scientists working with these particles must account for this mass increase in their calculations and experimental designs. The particles become much harder to steer with magnetic fields and require significantly more energy to accelerate them further. The observed behavior of these high-speed particles perfectly matches the predictions of special relativity, confirming the reality of relativistic mass increase. Without this effect, the particles would either reach the speed of light or behave in ways inconsistent with experimental observations. The idea of mass increasing with speed is deeply intertwined with the concept of relativistic momentum and energy. In special relativity, the classical definitions of kinetic energy and momentum also need to be modified. The total energy of an object at any speed is given by E Chakborn C2, which reduces to E Chas rest energy, plus a term for kinetic energy when the object is moving. The famous EMC2 equation specifically refers to the rest energy of a particle, the energy it possesses simply by virtue of its mass even when at rest. But it also elegantly describes the interconversion of a mass and energy at any speed. The implications of relativistic mass increase are profound. First, it establishes c as the universal speed limit for any object composed of matter. This means interstellar travel at light speed is impossible for spaceships with mass, and even approaching it would require immense, almost unimaginable amounts of energy. Second, it highlights the deep connection between mass and energy. The energy put into accelerating an object effectively becomes part of its mass, increasing its inertia. This blurring of lines between mass and energy is a cornerstone of modern physics and has been directly applied in understanding nuclear reactions, where a tiny amount of mass can be converted into a tremendous amount of energy. Third, it confirms the consistency and predictive power of special relativity. The theory's predictions, though counterintuitive, are consistently borne out by high-energy experiments, demonstrating that space, time, and mass are not independent absolutes, but are dynamically interwoven concepts that change depending on relative motion. all constrained by the ultimate constant of the speed of light. The phenomenon of mass increase with velocity is a testament to the fact that our universe operates under rules that transcend common sense at extreme speeds, making the speed of light an unbreachable barrier for anything material. One of the most widely recognized and profoundly impactful equations in all of physics is ERE-mc2. This simple-looking formula, formulated by Albert Einstein as part of his special theory of relativity in 1905, reveals a deep and fundamental connection between energy, E, and mass, m. It is not just a mathematical curiosity, it states that mass and energy are, in essence, two different forms of the same underlying entity, capable of being converted into one another. The C2 in the equation, representing the speed of light squared, acts as a colossal conversion factor, indicating that even a tiny amount of mass holds an enormous amount of intrinsic energy, and conversely, a vast amount of energy can manifest as a small amount of mass. Before Einstein, energy and mass were considered separate and distinct concepts, each conserved independently. The law of conservation of energy stated that energy could neither be created nor destroyed, only transformed from one form to another, like chemical to thermal or potential to kinetic. Similarly, the law of conservation of mass stated that mass could neither be created nor destroyed in chemical reactions. These principles were cornerstones of classical physics. However, the revolutionary insights of special relativity changed this fundamental understanding. Einstein's special theory of relativity was built upon two postulates. The laws of physics are the same for all observers in uniform motion, and the speed of light in a vacuum is constant for all observers. As a consequence of these postulates, Einstein showed that the familiar concepts of space, time, and mass are not absolute, but are relative to the observer's motion. The equation E-mc2 emerged as a direct and unavoidable consequence of these new understandings. To grasp the meaning of E-mc2, it helps to understand how Einstein arrived at it. In classical physics, an object at rest has no kinetic energy. Its energy is often thought of in terms of its potential energy or internal energy. However, Einstein's theory showed that even an object at rest possesses a vast amount of inherent energy simply by virtue of its mass. This is called rest energy. Consider the relationship between mass, momentum, and energy in special relativity. As we have discussed, special relativity predicts that an object's mass increases as its speed increases, approaching infinity as its speed approaches the speed of light. This relativistic mass increase implies that as you try to accelerate an object, more and more of the energy you put in goes into increasing its mass rather than its speed. Einstein's derivation involved considering how energy and momentum are conserved in various interactions, particularly when viewed from different inertial frames of reference. He found that for momentum and energy to be conserved consistently across all such frames, mass and energy had to be interchangeable. The total energy of a particle, including its rest energy and kinetic energy, is given by a more complex relativistic energy equation. However, the ESMC2 formula represents the simplest case, the energy contained within an object when it's at rest, meaning when its velocity, v, is 0. In the equation, E stands for energy, m stands for mass, and c stands for the speed of light in a vacuum. The C2 term is critical. The speed of light is an incredibly large number, approximately 300 million meters per second. Squaring this number, multiplying it by itself, results in an even more immense number, 9 times 10 to the power of 16 square meters per square second. This enormous conversion factor means that even a very small amount of mass corresponds to a colossal amount of energy. Let us consider a practical example. Imagine 1 kilogram of mass. If this entire 1 kilogram could be converted into energy, the amount of energy produced would be E, 1 kilogram times 300 million meters per second, squared E, 1 kilogram times 9 times 10 to the power of 16 square meters per square second, E just 9 times 10 to the power of 16 joules. To put this into perspective, 9 times 10 to the power of 16 joules is an enormous quantity of energy. It is roughly equivalent to the energy released by the detonation of 20 million tons of TNT, similar to a very large nuclear weapon. This immense energy contained within ordinary matter is why ERMC2 is often associated with atomic bombs and nuclear power. The equation means that mass can be converted into energy, and energy can be converted into mass. This interconversion is not just theoretical, it occurs in various physical processes. 1. Nuclear fission. This is the process used in nuclear power plants and atomic bombs. A heavy atomic nucleus, such as uranium or plutonium, splits into lighter nuclei. The total mass of the resulting lighter nuclei is slightly less than the mass of the original heavy nucleus. This missing mass has been converted into a tremendous amount of kinetic energy of the fission products, which then manifests as heat and radiation. For example, in the fission of one atom of uranium-235, the mass deficit is tiny, but the energy released per atom is enormous. 2. Nuclear fusion. This is the process that powers the sun and other stars, and is the basis for hydrogen bombs. Light atomic nuclei such as isotopes of hydrogen, deuterium and tritium, combine or fuse to form a heavier nucleus like helium. The mass of the resulting helium nucleus is slightly less than the combined mass of the original light nuclei. This mass difference is converted into a vast amount of energy, which is released as heat and light. Fusion reactions release even more energy per unit mass than fission reactions. 3. Annihilation of matter. Antimatter. When a particle meets its antiparticle, for example an electron meets a positron, they mutually annihilate each other. Their entire mass is converted into pure energy, typically in the form of gamma-ray photons. This is the most efficient known process for converting mass into energy, with 100% of the mass being converted. This is used in medical imaging such as positron emission tomography or PET scans. 4. Particle creation. Conversely, energy can be converted into mass. In high-energy physics experiments at particle accelerators, vast amounts of kinetic energy are imparted to colliding particles. When these particles collide, some of their kinetic energy can be converted into new particles, and their antiparticles, which have mass. This demonstrates the reverse process of energy turning into mass. 5. Binding energy. When atomic nuclei are formed, protons and neutrons are bound together. The mass of a nucleus is always slightly less than the sum of the masses of its individual protons and neutrons when they are separated. This mass defect represents the energy released when the nucleus forms, known as the binding energy. This energy holds the nucleus together. If you want to break a nucleus apart, you must put that binding energy back in, which means converting energy back into the missing mass. It is important to clarify that EMC2 does not mean that mass turns into energy in a literal sense, like water turning into ice. Rather, it means that mass is a form of energy, and energy is a form of mass. They are two manifestations of the same fundamental quantity. When mass disappears in nuclear reactions, it has not vanished from existence. It has simply changed its form into other types of energy, such as kinetic energy of particles or electromagnetic radiation, like gamma rays. The total amount of mass energy in a closed system remains conserved. This means that the combined law of conservation of mass energy replaced the separate conservation laws of mass and energy. The equation also contributes to the concept of relativistic mass, though modern physics prefers to speak of rest mass and total energy. As an object's speed increases, the energy put into accelerating it not only increases its kinetic energy, but also, in a sense, increases its effective or relativistic mass. This explains why it becomes harder and harder to accelerate an object as it approaches the speed of light. The energy of motion, kinetic energy, itself contributes to the object's total mass energy content. The discovery of ERMC2 fundamentally altered our understanding of the universe. It revealed the immense energy locked within matter, leading to both the awesome power of nuclear weapons and the promise of nuclear power as an energy source. Beyond these practical applications, it provided a deeper insight into the interconnectedness of fundamental physical quantities. It showed that what we perceive as mass is just one form that energy can take, and that the speed of a light c is not just a speed limit, but also the universal constant that links these two fundamental aspects of reality. This equation is a cornerstone of special relativity, profoundly shaping modern physics, and providing a new lens through which to view the structure and dynamics of the cosmos. One of the most remarkable and foundational principles stemming from Albert Einstein's special theory of relativity, introduced in 1905, is the unwavering cosmic speed limit. Nothing in the universe that possesses mass can ever reach or exceed the speed of light in a vacuum. This is not a mere technological hurdle that humanity might one day overcome. It is an intrinsic, unbreakable law of physics that dictates the very structure of our reality. The fundamental reasons for this impenetrable barrier are deeply embedded within the relativistic framework that governs how mass, energy, momentum, and space-time itself behave at extreme velocities. Understanding this limit requires a departure from our everyday intuitions, which are largely shaped by experiences at speeds vastly slower than that of light. In the realm of classical Newtonian physics, which had dominated scientific thought for over 2 centuries prior to Einstein, there was no theoretical upper bound to an object's speed. According to Newton's laws of motion, if a continuous force were applied to an object, it would, in principle, accelerate indefinitely, eventually surpassing any given speed, no matter how fast. The concept of velocity simply adding and subtracting linearly was also central to this classical view. For instance, if you were on a vehicle moving at 100 km per hour and you threw a ball forward at 10 km per hour relative to your vehicle, a stationary observer would measure the ball's speed as 110 km per hour. This straightforward arithmetic seemed to apply universally. However, as science advanced into the late 19th and early 20th centuries, inconsistencies began to emerge, particularly when dealing with the behaviour of light. James Clerk Maxwell's groundbreaking work in electromagnetism revealed that light is an electromagnetic wave, and his equations consistently predicted that its speed in a vacuum, a value commonly denoted as c, is constant, approximately 300,000 km per second. This constancy was a perplexing issue for classical physics because it did not fit the traditional velocity addition rules. Furthermore, the famous Michelson-Morley experiment of 1887, designed to detect a hypothetical ether wind that would cause variations in light speed as Earth moved through a stationary medium, yielded a surprising null result. Light speed appeared to be the same for all observers, regardless of their motion. This was the fundamental puzzle that Einstein confronted. Einstein's radical insight was to accept this observed constancy of the speed of light as a fundamental postulate of the universe, rather than trying to explain it away within the old framework. His special theory of relativity is built upon this premise, alongside the postulate that the laws of physics are the same for all observers in uniform motion. From these two deceptively simple ideas, a host of counterintuitive consequences emerge, directly explaining why c is an ultimate speed limit for anything possessing mass. The primary reason why no massive object can reach the speed of light stems from the phenomenon of relativistic mass increase. In classical physics, an object's mass is considered an inherent and unchanging property, regardless of its motion. Whether a baseball is at rest or flying through the air, its mass remains the same. However, special relativity dictates otherwise. As an object accelerates and its speed approaches the speed of light, its mass, as measured by an observer relative to whom the object is moving, increases. This is not an increase in the number of particles that make up the object, but rather an increase in its inertia, its resistance to further changes in motion. The object becomes heavier, in the sense that it requires more and more force to produce the same amount of acceleration. The mathematical relationship for this relativistic mass, m, is given by the formula m sum m0, 1, v2, c2. Here, m0 represents the object's rest mass, its mass when it is stationary relative to the observer, v is the object's speed, and c is the speed of light in a vacuum. Let us analyse what this equation reveals as an object's speed approaches c. At everyday speeds, where v is minuscule compared to c, the term v2c2 becomes an extremely small number, very close to 0. Consequently, the entire denominator, 1 v2c2, is practically equal to 1. This means that the relativistic mass m is almost identical to the rest mass mgo. This is why we do not observe any noticeable change in mass for cars, airplanes, or even rockets. Classical physics works perfectly well for these low-speed scenarios. However, as an object's speed v begins to increase and approaches a significant fraction of c, the term v2c2 becomes a non-negligible number, getting closer and closer to 1. As v2c2 approaches 1, the term 1 v2c2 approaches 0. When a number approaches 0, its square root also approaches 0. This means the denominator, 1 v2c2, becomes a very small number, getting closer and closer to 0. Now consider what happens when you divide the rest mass m del by a denominator that is approaching 0. As the denominator gets smaller and smaller, the result of the division gets larger and larger, tending towards infinity. If the object were to hypothetically reach the speed of light, meaning v equals c, then v2c2 would be exactly 1. The denominator would become 1, 1, 0, 0. According to mathematics, division by 0 yields an infinite result. Therefore, if an object with a non-zero rest mass were to reach the speed of light, its mass would become infinite. This concept of infinite mass has profound implications for acceleration. According to Newton's second law of motion, the force, F, required to accelerate an object is proportional to its mass, m, and its acceleration, a, or F ma. If the mass of an object becomes infinite, then an infinite amount of force would be required to produce any further acceleration, no matter how tiny that acceleration might be. Since it is physically impossible to generate an infinite force, or provide an infinite amount of energy, it becomes an absolute barrier. No amount of sustained pushing or propulsion can ever accelerate an object with a non-zero rest mass to the speed of light. The closer an object gets to c, the more resistant it becomes to further acceleration. This effect is not theoretical speculation. It is rigorously confirmed in high-energy physics laboratories around the world, particularly in particle accelerators. In these colossal machines, subatomic particles like electrons and protons are accelerated to speeds that are almost unfathomably close to the speed of light. For example, particles in the Large Hadron Collider can reach speeds of 99.9999999% of c. At such extreme velocities, their relativistic mass is thousands or even hundreds of thousands of times greater than their rest mass. An electron, for instance, which has a very tiny rest mass, can achieve an effective mass comparable to that of a small mosquito, or even a bacterium when accelerated to near light speed. The enormous amounts of energy pumped into these accelerators are not primarily increasing the particle's speed, but rather dramatically increasing their relativistic mass. Despite the immense energy inputs, these particles consistently fail to actually reach c. They only ever get infinitesimally closer. This experimental observation serves as direct and irrefutable proof of relativistic mass increase and the impossibility of reaching light speed for massive objects. The impossibility of faster-than-light travel for massive objects is also intrinsically linked to the concept of energy. The total energy of an object in special relativity is given by a more comprehensive equation than the simple kinetic energy of classical physics. It turns out that as an object gains speed, the kinetic energy required to further increase that speed escalates dramatically. The energy input does not solely translate into increased velocity. A significant portion of it gets converted into mass energy, according to E mc2. As a massive object approaches c, the kinetic energy needed to push it just a tiny bit faster approaches infinity. This means that an infinite amount of energy would be required to bring its velocity exactly to c. Since there is no infinite source of energy, the speed of light remains an unreachable threshold. Furthermore, the speed of light is not just a speed for particles of light, it represents the maximum speed at which any information or causal influence can propagate through the universe. This is a crucial concept known as causality. If it were possible for something to travel faster than light, it would violate the principle of causality, meaning that an effect could potentially occur before its cause. Imagine a scenario where a signal is sent from point A to point B. If this signal travelled faster than light, it might arrive at point B before it was even sent from point A, when viewed from a different frame of reference. This would create logical paradoxes, potentially allowing for communication with the past, which is inconsistent with all observed laws of physics. The speed of light acts as a cosmic traffic cop, ensuring that the fundamental order of cause and effect is preserved throughout the universe. This strict speed limit has profound implications for various aspects of physics and our broader understanding of the cosmos. 1. Interstellar travel. The speed of light limit imposes a severe constraint on our ability to travel between stars and galaxies. Even if we could design a spacecraft capable of accelerating to 99.99% of c, journeys to even our nearest stellar neighbours would still take many years from the perspective of those on Earth, while time dilation would mean less time would pass for the travellers on board the fast-moving spacecraft. They would age less. The vast cosmic distances mean that such trips would still be incredibly long and require immense energy, fundamentally limiting how far and fast humanity can spread through the galaxy in a single lifetime measured by Earth time. 2. Communication across space. All forms of communication across astronomical distances are bound by the speed of light. When scientists receive radio signals from distant space probes, or when astronomers observe light from distant galaxies, they are always seeing these objects as they were in the past, when the light or signal began its journey. For example, a command sent to the Voyager probes, which are now far beyond our solar system, takes many hours to reach them, and the confirmation signal takes just as long to return. There is no way to instantly communicate across such vast gulfs of space. 3. Particle physics and accelerator design. As previously mentioned, the understanding of relativistic mass increase and the speed limit is absolutely critical in the design and operation of particle accelerators. Engineers and physicists must precisely account for these relativistic effects to successfully guide and collide particles at near light speeds. Without this understanding, the particles would simply not behave as observed, and the machines would not function. 4. The nature of massless particles. While objects with rest mass cannot reach c, particles that are inherently massless, such as photons, particles of light, and gluons, which mediate the strong nuclear force, are fundamentally different. They are not subject to relativistic mass increase because their rest mass is zero. These particles are born travelling at the speed of light and can only exist at that speed. They cannot be slowed down to less than c, nor can they be brought to rest. Their very existence is inextricably tied to moving at the speed of light, representing the limit of energy propagation without mass. To truly grasp the profound implications of the speed of light as an ultimate cosmic limit, it is illuminating to consider a hypothetical scenario. What would it be like to travel at the speed of light? This is a purely imaginative exercise, as it is impossible for anything with mass to actually reach c. However, by exploring the logical consequences of Einstein's special theory of relativity at this extreme velocity, we can gain a deeper appreciation for how space and time are fundamentally altered when observed from such a unique vantage point. This perspective is essentially what light itself experiences, as photons are massless particles that inherently travel at c. From the standpoint of an object or particle travelling at the speed of light, the universe would transform in ways that defy our everyday intuition. The two key relativistic effects, time dilation and length contraction, would become absolute. First, let us consider time dilation from the perspective of light. Time dilation dictates that as an object's speed approaches c, time for that object appears to slow down relative to an observer at rest. The mathematical formula for time dilation shows that as velocity v approaches the speed of light c, the factor by which time is stretched approaches infinity. If v were equal to c, the denominator in the time dilation formula would become zero, implying that time would completely stop. So, from the perspective of a photon, which always travels at the speed of light, time essentially ceases to exist. A photon emitted from a distant star, say 1 billion light-years away, and travelling across the vast expanse of the universe to reach your eye, experiences no passage of time during its entire journey. For that photon, the moment it was emitted and the moment it is absorbed are the same instantaneous event. There is no journey in time, no duration, no aging. The billion years that pass for observers on Earth or in the galaxy are simply non-existent from the photon's own frame of reference. It experiences no ticks of a clock. This concept can be quite challenging to wrap our minds around. We are accustomed to time being an ever-flowing universal constant. But for light, time is utterly compressed to zero. This is one of the reasons why photons are able to travel such immense distances across the cosmos without ever decaying, even though they are quantum particles. If they experienced time, even for a fraction of a second, they would quickly decay or lose coherence. Their existence is instantaneous travel. Second, consider length contraction from the perspective of light. Length contraction states that an object's length in its direction of motion appears to shrink as its speed approaches c, as seen by a stationary observer. The mathematical formula for length contraction also involves the same factor that drives time dilation. As v approaches c, the contraction factor approaches 0. If v were equal to c, the object's length in the direction of motion would contract to 0. Applying this to a photon, it means that from the photon's perspective, the entire universe along its direction of travel is instantaneously compressed to 0 length. If a photon is travelling from a star to Earth, the enormous distance of millions or billions of kilometres between the star and Earth collapses to nothing from the photon's point of view. It's as if the star and Earth are directly adjacent. The journey spatially is instantaneous and 0 in length. This is why photons don't travel in the conventional sense of traversing a distance over a duration of time. For a photon, there is no elapsed time and no traversed distance in its own frame. Its emission and absorption occur at the same space-time point for the photon itself. This extreme contraction means that from a photon's perspective, the entire universe is flattened into a two-dimensional plane perpendicular to its direction of travel. There is no forward or backward movement through space. Rather, it is an instantaneous arrival across a 0-length distance. It is crucial to re-emphasize that this perspective is a hypothetical mental construct, as it's impossible for any observer with mass to actually reach the speed of light. We cannot physically ride a photon. However, thinking about these extreme conditions helps to illustrate the fundamental nature of space-time according to special relativity. The Lorentz transformations, the mathematical rules that govern how measurements of space and time change between different inertial frames, become singular, infinite, or 0 at the speed of light. This mathematical singularity reinforces the idea that an observer's frame of reference simply cannot exist at the speed of light if that observer has mass. What are the implications of this photon's perspective? 1. No proper frame of reference. Since time stops and lengths shrink to 0, a photon cannot have a proper reference frame in the same way a massive object does. There is no clock ticking for it, and no ruler it carries. The very concepts of length and time, as we understand them, break down at c. This is why we always talk about the speed of light being c, as measured by observers who are not travelling at c. 2. Light is always c. The fact that photons always move at c in any inertial frame of reference is consistent with this perspective. If time effectively stops for a photon, it cannot slow down. If distances effectively shrink to 0, there is no journey that takes time. This inherent behaviour is part of why c is a constant. Light isn't accelerating to c, it simply is c. 3. Causality and instantaneity. The instantaneity of events from a photon's perspective also highlights its role in causality. Since photons are the carriers of electromagnetic interactions and information, their zero-time, zero-distance experience ensures that interactions occur without delay from their point of view, preserving the causal structure of the universe. This hypothetical journey to the speed of light, therefore, is not a vacation destination for a massive spaceship, but a powerful intellectual tool. It helps us understand why c is not just a fast speed, but a boundary where the very fabric of reality behaves in extreme and counterintuitive ways. It underscores that space and time are not fixed backdrops against which events unfold, but dynamic, interconnected entities that stretch and contract depending on relative motion, all to uphold the fundamental principle that the speed of light in a vacuum is invariant for all observers. The photon's experience, where time is frozen and distance annihilated, is the most extreme illustration of this relativistic universe. It reveals that the speed of light is not just a limit for moving objects, but also a fundamental property that defines the nature of duration and extent themselves. Light, a phenomenon so central to our perception of the world, exhibits a peculiar and fundamental characteristic. it always travels at a constant speed in a vacuum, known as c, approximately 300,000 kilometers per second. This speed is not merely a fast velocity, it is an ultimate cosmic speed limit. The reason light travels at this precise speed, and why it can never be at rest or move slower than c, lies deep within its fundamental nature as a photon, the particle of light, and the laws of special relativity formulated by Albert Einstein in 1905. To understand why photons behave this way, we must first grasp the concept of rest mass. In classical physics, mass is an inherent property of an object that resists changes in its motion. An object at rest has a certain mass, and that mass remains constant whether the object is stationary or moving. This concept of mass is directly linked to an object's inertia and its gravitational pull. However, special relativity introduced a more nuanced understanding of mass, distinguishing between rest mass and relativistic mass. While modern physics often prefers to talk about a particle's rest mass and its total energy, the concept of relativistic mass is still useful for intuition. The rest mass, often denoted as ρ, is the mass an object possesses when it is not moving relative to an observer. For everyday objects, and even subatomic particles like electrons and protons, this rest mass is a positive, non-zero value. The crucial characteristic of a photon is that it has zero rest mass. This is not an approximation, it is a fundamental property of the photon. Unlike an electron or a proton, a photon simply does not possess any mass when it is at rest. In fact, a photon can never be at rest. This is a profound distinction from all particles that make up ordinary matter. The implications of having zero rest mass are far-reaching and directly explain the photon's unvarying speed. In special relativity, the total energy, E, of any particle is related to its momentum, p, and its rest mass, m0, by a fundamental equation, E2 down pc2 plus m0c2 This equation combines the concepts of mass and energy within the relativistic framework. Let us analyse this equation for a particle with zero rest mass, like a photon. If m0 equals 0, then the term mc2 also equals 0. The equation then simplifies dramatically to E2 skirl pc2. Taking the square root of both sides gives E pc. This simplified equation is critical. For a particle with zero rest mass, its energy is entirely determined by its momentum, p, multiplied by the speed of light, c. It means that a massless particle carries energy solely by virtue of its motion. If it were to have zero momentum, it would have zero energy, which effectively means it would not exist. A photon's existence is intrinsically linked to its momentum and thus its motion. This leads directly to the conclusion that a photon cannot exist at rest. If a photon were to be brought to rest, meaning its velocity v is 0 and thus its momentum p is 0, its energy E would also become 0, since E equals pc. A particle with zero energy does not interact with anything and cannot be observed. It essentially ceases to exist as a distinct entity. Therefore, the very condition for a photon's existence is that it must possess momentum and energy, which means it must be in motion. It cannot shed its momentum and energy without ceasing to be a photon. Furthermore, a photon cannot travel at any speed slower than c. If a photon were to travel at a speed v less than c, it would again imply that it would have a non-zero rest mass, which contradicts its fundamental nature. The relativistic energy-momentum relation inherently connects a particle's speed to its mass. For a particle to travel slower than c, its rest mass must be greater than 0. Since a photon has zero rest mass, it is simply not allowed to travel at any speed other than c. It is not a choice for the photon. It is an intrinsic aspect of its identity. This behaviour is intimately connected to the extreme relativistic effects of time dilation and length contraction when approaching the speed of light. From the perspective of an observer outside the photon, as an object's speed v approaches c, time for that object slows down, time dilation, and distances in its direction of motion shrink, length contraction. At the exact speed of light, c, the mathematical formulas for time dilation and length contraction predict that time would essentially stop, and lengths in the direction of motion would shrink to zero. While it is impossible for an observer with mass to experience being at C, we can extrapolate the consequences for a photon. For a photon, there is no passage of time from its emission to its absorption. The journey, no matter how many light years long, is instantaneous for the photon itself. Similarly, the vast distances it traverses are contracted to zero length in its direction of travel. This means a photon does not travel in the conventional sense of covering a distance over a duration of time. Its emission and absorption are, in a sense, the same event for the photon. This extreme relativistic effect is a direct consequence of its zero-rest mass. The photon's unvarying speed is also deeply tied to its role as the quantum of the electromagnetic field. In quantum field theory, fundamental forces are mediated by the exchange of particles. The electromagnetic force, responsible for light, electricity, and magnetism, is mediated by photons. These photons are the fundamental excitations, or quanta, of the electromagnetic field. For the electromagnetic force to propagate at C, its mediating particle, the photon, must also travel at C. If photons could travel slower or be at rest, the electromagnetic force itself would behave differently, which is not observed. The creation and destruction of photons are also consistent with their zero rest mass and constant speed. Photons are emitted when charged particles, like electrons, change energy levels, and they are absorbed when their energy is transferred to other particles. A photon is not a persistent object that can slow down or speed up. It is created travelling at C and annihilates upon interaction, transferring its energy. When light passes through a material medium, such as glass or water, it appears to slow down. However, this is not because the individual photons are slowing down. Instead, it is because the photons are constantly being absorbed by atoms in the material and then re-emitted. The time delay comes from these absorption and re-emission processes and the propagation through the material, not from the individual photons themselves travelling slower than c within the medium. Between interactions, they still travel at c. The concept of a photon having zero rest mass has profound implications for its momentum. Even though it has no rest mass, a photon still carries momentum. This is given by the simplified relativistic relation E, Raya, Pc, which can be rearranged to P, Gra, E, C. So, a photon's momentum is simply its energy divided by the speed of light. This momentum is what allows photons to exert pressure, radiation pressure, and to transfer energy effectively despite being massless. This momentum is also why light can push on objects, even though it has no rest T mass. The existence of momentum without rest mass is a uniquely relativistic concept. The concept of empty space might seem straightforward. A void, nothingness, the absence of matter or energy. However, in the context of light and electromagnetism, empty space is far from passive. It possesses fundamental properties that actively determine and limit the speed at which light can travel through it. These properties are not tied to any hypothetical medium like the luminiferous ether, but are intrinsic characteristics of space itself. Specifically, these properties are the electrical permittivity of free space and the magnetic permeability of free space. The brilliant insight of James Clerk Maxwell in the mid-19th century was to mathematically derive the speed of light directly from these seemingly unrelated electrical and magnetic constants. Before Maxwell's work, the idea of empty space transmitting forces, or waves, was often problematic for scientists. Action at a distance, where forces like gravity or magnetism appeared to act instantaneously across empty space, was conceptually challenging. The concept of a medium, like the air for sound or water for ripples, provided a more intuitive explanation for wave propagation. This intuition led to the belief in a luminiferous ether for light, a ubiquitous, invisible substance filling the void. However, Maxwell's equations and later experimental evidence would reveal a different picture. Space itself, even when empty of matter, has inherent electromagnetic characteristics that govern light's behaviour. Let us delve into these two fundamental constants of empty space. First, the electrical permittivity of free space, denoted by the Greek letter epsilon naught, E0. This constant quantifies how an electric field permeates, or permits, empty space. More precisely, It describes the ability of a vacuum to store electric energy when an electric field is present, or the resistance of empty space to the formation of an electric field. It tells us how much electric field is generated by a given electric charge. In Coulomb's law, which describes the force between two electric charges, E0 appears in the denominator, indicating that a larger permittivity means a weaker electric force for a given amount of charge, because the field is more spread out or permitted by the vacuum. Its numerical value is approximately 8.854 times 10 to the power of minus 12 farads per meter. This constant is a measure of the electric properties of the vacuum. Second, the magnetic permeability of free space, denoted by the Greek letter mu0, m0. This constant quantifies how a magnetic field passes through, or permits, empty space. It describes the ability of a vacuum to support the formation of a magnetic field, or how much magnetic field is generated by a given electric current. In Ampere's law, which describes how electric currents create magnetic fields, m0 appears in the numerator, indicating that a larger permeability means a stronger magnetic field for a given current. Its numerical value is approximately 1.257 times 10 to the power of minus 6 henries per meter. This constant is a measure of the magnetic properties of the vacuum. It is crucial to understand that these two constants, E0 and M0, were initially determined through entirely separate experiments involving static electric charges, electric currents, and magnets. They describe phenomena that, at first glance, have nothing directly to do with the speed of light itself. E0 governs how electric fields radiate from charges, and M0 governs how magnetic fields loop around currents. They are fundamental properties of the vacuum's response to electric and magnetic influences. Maxwell's monumental achievement was to take the existing laws of electricity and magnetism, which included empirical findings from scientists like Coulomb, Ampere, and Faraday, and synthesize them into a unified mathematical theory. When Maxwell formulated his complete set of 4 equations that describe the behavior of electric and magnetic fields, he made a crucial theoretical addition. He proposed that a changing electric field could generate a magnetic field. This displacement current term was purely theoretical at the time, but it provided the missing piece that allowed his equations to predict the existence of electromagnetic waves. The true stroke of genius came when Maxwell examined his unified equations in empty space, free from electric charges or currents. He found that these equations mathematically implied that disturbances in the electromagnetic field could propagate as waves. More astonishingly, the speed, let's call it v, at which these theoretical electromagnetic waves should travel was inherent in the structure of the equations, determined solely by E0 and M0. The derived speed was given by the simple and elegant formula v 1 mv0. When Maxwell substituted the experimentally determined numerical values for E0 and M0 into this formula, the calculated speed was approximately 300 million meters per second, 300,000 kilometers per second, or about 186,000 miles per second. This numerical value was strikingly close to the independently measured speed of light, which had been determined through astronomical observations by Roemer and terrestrial experiments by Fizeau and Foucault. This astonishing agreement was not a coincidence. It led Maxwell to the revolutionary conclusion that light itself was an electromagnetic wave. This meant that the light we see, along with other forms of radiation like radio waves, microwaves, and X-rays, are all part of an electromagnetic spectrum, consisting of oscillating electric and magnetic fields propagating through space at a speed dictated by the fundamental properties of the vacuum. The significance of this derivation is immense. It showed that the speed of a light is not an arbitrary value. It is a direct consequence of the way electric and magnetic fields behave in empty space. The constants E0 and M0 are not just abstract numbers, they are precise measurements of how permissive empty space is to electric and magnetic fields. In essence, the speed of a light is fixed because the vacuum itself has these fundamental, unchanging electromagnetic properties. This revelation fundamentally altered the concept of empty space. It was no longer seen as a passive void but as an active entity, with inherent physical characteristics that govern the propagation of light. While Maxwell's initial work was interpreted within the context of a luminiferous ether, the medium through which these electromagnetic waves were thought to travel, later developments, particularly the null result of the Michelson-Morley experiment and Einstein's special theory of relativity, discarded the ether. However, the fundamental role of E0 and M0 in determining light speed remained. They are properties of the vacuum itself, not of a hypothetical material medium. In a sense, empty space provides the fabric through which electromagnetic waves ripple. The speed at which these ripples propagate is determined by how easily electric fields can be established and changed, governed by E0, and how easily magnetic fields can be established and changed, governed by M0. If E0 were larger, it would be harder to establish electric fields, potentially slowing down light. If M0 were smaller, it would be easier for magnetic fields to form, which also affects the speed. The specific combination of their values yields the observed speed of light. This intrinsic relationship also explains why the speed of light changes when it passes through material media like water or glass. In a material, light interacts with the electrons and atomic nuclei. These interactions effectively change the overall permittivity and permeability of the medium. The electrons in the material respond to the oscillating electric and magnetic fields of the light wave, absorbing and re-emitting photons. This process takes time and is what effectively slows down the light. The speed of light in a material is therefore less than c, and it depends on the electrical and magnetic properties of that specific material. The value c remains the absolute speed only in a perfect vacuum, where there are no particles to interact with the electromagnetic fields. The constancy of c in a vacuum, derived from E0 and M0, suggests that these fundamental properties of empty space are themselves constant throughout the universe. There is no evidence that E0 or M0 vary in different regions of the cosmos. This universal constancy of the vacuum's electromagnetic properties means that the speed of light is truly a universal constant, unaffected by location, time, or the motion of sources or observers. It is a fundamental property of the universe's basic structure,